What happens when a galaxy grows so large that it stretches across a distance equivalent to 160 Milky Way galaxies laid end to end? In February 2022, astronomers announced the discovery of Alcyonius, a radio galaxy whose lobes extend 16.3 million light-years from tip to tip. To put that in perspective, the distance from Earth to the Andromeda Galaxy, our nearest large galactic neighbour, is 2.5 million light-years. Alcyonius spans more than 6 times that distance. This isn't about the visible galaxy itself, which remains relatively modest in size. This is about the colossal structures emanating from its core, invisible to optical telescopes but blazing across radio wavelengths with an intensity that speaks to processes operating at scales that challenge our models of how galaxies behave. The discovery raises immediate questions. How does a single galaxy produce structures larger than the spaces between galaxy clusters? What kind of energy output sustains features visible across such distances? And perhaps most importantly, why did it take until 2022 to find an object this massive? The answer to that last question reveals as much about the limitations of our observational tools as it does about the nature of the object itself. Alcyonius wasn't hiding. It was broadcasting its presence across the cosmos for hundreds of millions of years. We simply weren't looking in the right way, at the right frequencies, with instruments sensitive enough to piece together something so large that it exceeds the field of view of most radio surveys. Giant radio galaxies represent a category of objects that occupy a strange position in astronomy. They're simultaneously enormous and nearly invisible, detectable only through specialized equipment tuned to frequencies far below what human eyes can perceive. Alcyonius sits 3 billion light-years away, a distance that places it firmly in the realm of deep cosmological surveys. At that range, even a structure 16 million light-years across appears as a faint smudge, requiring careful data processing to distinguish from background noise. The jets responsible for these lobes originate from a supermassive black hole at the galaxy's centre, but the mechanism by which that black hole creates and maintains structures of this scale remains an open question in astrophysics. The first radio galaxies entered scientific literature in the 1950s, when astronomers began systematically surveying the sky at wavelengths far longer than visible light. What they found challenged existing notions of galactic structure. Certain galaxies, often elliptical in shape and relatively quiet in optical observations, revealed themselves as powerful radio sources when viewed through the emerging technology of radio interferometry. These weren't just bright points of radio emission, they displayed distinctive morphologies, with twin lobes of radio-emitting plasma extending far beyond the visible boundaries of their host galaxies. The symmetry was striking. 2 enormous clouds of energized particles mirror images of each other positioned on opposite sides of the galactic core. The explanation, when it emerged, pointed to one of the most energetic phenomena in the universe. At the heart of these radio galaxies sits a supermassive black hole, an object containing millions to billions of times the mass of our Sun, compressed into a region smaller than our solar system. When matter falls towards such a black hole, it doesn't simply vanish beyond the event horizon. The infalling material forms an accretion disk, a swirling maelstrom of gas and dust heated to millions of degrees by friction and gravitational compression. This disk becomes one of the brightest objects in the universe, outshining entire galaxies despite occupying a space no larger than the distance from the Sun to Pluto. But the accretion disk itself isn't what creates the radio lobes. That role belongs to the jets. From the regions immediately surrounding the black hole's event horizon, something remarkable occurs. A fraction of the infalling matter doesn't cross into the black hole but instead gets channeled along powerful magnetic field lines that thread through the accretion disk. These fields, twisted and amplified by the rotation of both the disk and potentially the black hole itself, act as cosmic particle accelerators. Material caught in these fields gets funneled into 2 narrow beams pointing in opposite directions, perpendicular to the disk's plane. The particles in these jets reach velocities approaching the speed of light, and the jets themselves maintain their coherence across distances that dwarf the galaxy producing them. When we observe a radio galaxy, we're seeing the aftermath of this process, the points where these relativistic jets slam into the thin gas of intergalactic space and create vast bubbles of radio-emitting plasma. The physics governing these jets remains an area of active research. the energy required to accelerate particles to near light speed and maintain that acceleration across millions of light years exceeds the total energy output of thousands of normal galaxies. Yet the process appears remarkably stable. Jets can remain active for tens or even hundreds of millions of years, continuously feeding the lobes with fresh material. The magnetic fields threading through these jets prevent them from dissipating immediately into the surrounding space. Instead, they form tightly collimated streams, often narrower than a few thousand light years across despite extending for millions of light years in length. High-resolution radio observations reveal intricate structure within these jets, knots and filaments, where the magnetic fields strengthen or where the jets encounter denser pockets of intergalactic gas. When a jet terminates, it creates what astronomers call a hotspot, a region where the jet's energy dumps into the intergalactic medium. These hotspots mark the leading edge of the radio lobes, the points where relativistic particles plow into previously undisturbed gas. The collision generates shock waves, heating the gas and accelerating particles to extreme energies. These particles, primarily electrons, spiral around magnetic field lines and emit synchrotron radiation, the characteristic signature of radio galaxies. The radiation spans a broad range of frequencies, but it peaks in the radio portion of the spectrum, making these objects far brighter in radio wavelengths than in visible light. The lobes themselves extend back from the hotspots toward the galactic core, filled with particles that have lost energy over time as they radiate away their momentum. Older lobes appear fainter and more diffuse as the particles within them age and the synchrotron radiation weakens. Radio galaxies come in different classifications based on their structure and luminosity. Phaneroff-Riley Class 1 galaxies display relatively bright cores with lobes that fade gradually toward their edges. Phaneroff-Riley Class 2 galaxies, by contrast, show brighter emission at the edges of their lobes where the jets terminate in prominent hotspots. This classification correlates with jet power. More powerful jets create Class 2 morphologies, driving further into the intergalactic medium and creating more dramatic hotspot features. Alcyonius belongs to this second category, though its extreme size places it in a subset that has drawn increasing attention from researchers studying the outer limits of galactic activity. The term giant radio galaxy entered astronomical nomenclature to describe objects whose radio lobes extend beyond 4 million light-years. This threshold, while somewhat arbitrary, captures galaxies whose structures exceed typical scales by significant margins. Most radio galaxies display lobes spanning hundreds of thousands to perhaps 1 or 2 million light-years. Giant radio galaxies push past this range, and until recently, only a few hundred examples were known. The rarity suggested that special conditions were required, either in the galaxy itself, in its environment, or in the history of its central black hole's activity. Alcyonius, at 16.3 million light-years, doesn't just exceed the threshold for giant radio galaxy status, it surpasses the previous record holder by roughly 30%, a substantial margin in a field where size records tend to be broken by smaller increments. The discovery came through the LOFAR survey, the Low Frequency Array, a radio telescope network distributed across Europe with its core concentration in the Netherlands. LOFAR operates at frequencies between 10 and 240 MHz, significantly lower than most radio astronomy facilities. This low-frequency range proves crucial for detecting giant radio galaxies. The synchrotron radiation from age particles in distant lobes shifts toward lower frequencies as the electrons lose energy. Older, more extended lobes glow brightest at the frequencies LOFAR was designed to detect. Higher frequency surveys miss these structures entirely or detect only their brightest inner regions. LOFAR's sensitivity to low-frequency emission allows it to map the full extent of radio lobes that would otherwise remain partially invisible, revealing populations of giant radio galaxies that earlier surveys had overlooked. Alcyonius appeared in LOFAR data as a pair of enormous lobes stretching across the sky, each lobe displaying the characteristic spectrum and morphology of aged synchrotron emission. The host galaxy, catalogued as SDSS-J, 081421.68 plus 5, 22410.0, sits at a redshift of 0.247, translating to a light travel distance of approximately 3 billion light-years. At that distance, the angular size of the lobes on the sky spans several arc minutes, a scale large enough to be resolved clearly by LOFAR's interferometric arrays, but small enough that piecing together the full structure required careful data processing and the combination of multiple pointings. The researchers who identified Alcyonius were conducting a systematic search for giant radio galaxies in LOFAR data, specifically looking for extended low-surface brightness emission that previous surveys might have missed. The host galaxy itself offers few clues to explain why it produces such extraordinary structures. SDSS-J 08142 1.68 plus 5 2 2 410.0 appears as an elliptical galaxy with a mass of roughly 240 billion solar masses, placing it in the category of large but not exceptional elliptical galaxies. Its stellar population shows characteristics typical of galaxies that have long since ceased active star formation, dominated by older, redder stars that have been evolving for billions of years. Optical observations reveal no obvious signs of recent mergers or interactions with neighbouring galaxies, no tidal streams or distorted morphology that might suggest a traumatic history. The galaxy sits in a relatively sparse region of space, not embedded within a dense galaxy cluster, where environmental effects might play a significant role. By most measures, it appears unremarkable, just another massive elliptical galaxy among billions scattered across the observable universe. The central black hole powering Alcyonius has been estimated at around 400 million solar masses based on correlations between black hole mass and the properties of the host galaxy. This places it well within the range of supermassive black holes found in similar galaxies, neither unusually large nor unusually small. The relationship between black hole mass and radio lobe size shows no simple correlation across the population of radio galaxies. Some of the most massive black holes produce modest radio structures, while black holes of intermediate mass occasionally generate giant lobes. Whatever factor determines final lobe size, it doesn't appear to be black hole mass alone. The accretion rate, the amount of matter falling onto the black hole per unit time, plays a crucial role in determining jet power, but even this relationship proves complex. A black hole can produce powerful jets while accreting at relatively modest rates if the accretion occurs in a particular geometric configuration that efficiently extracts rotational energy. One critical parameter involves the spin of the black hole itself. General relativity predicts that rotating black holes drag space-time around them in a process called frame dragging. The faster the black hole spins, the more dramatic this effect becomes. Magnetic field lines threading through the ergosphere, the region just outside the event horizon where space-time rotation becomes unavoidable, can tap into the black hole's rotational energy through a mechanism known as the Blandford-Znajek process. This process converts the black hole's spin into electromagnetic energy that powers the jets, potentially allowing for jet luminosities that exceed what accretion energy alone could provide. A maximally spinning black hole can theoretically extract up to 29% of its rest mass energy through this mechanism, an efficiency far exceeding anything achievable through nuclear fusion. Whether the black hole at the centre of Alcyonius possesses particularly high spin remains unknown, but the sheer size of its lobe suggests that its jets have maintained high power output for an extended period. The duration of jet activity required to create lobes 16 million light-years across depends on how fast the jets propagate through intergalactic space. Jets don't expand at the speed of light despite containing relativistic particles. The jets themselves plough through the intergalactic medium at speeds typically ranging from a few percent to perhaps 10% of light speed. The resistance they encounter depends on the density of gas in their path. In dense environments, jets slow down more quickly as they push against greater amounts of material. In sparse regions, they can propagate more freely, creating larger structures before stalling. Calculating the age of Alcyonius's lobes requires estimating both the jet propagation speed and the density of the intergalactic medium through which they've travelled. Researchers studying Alcyonius estimate that the lobes have been growing for several hundred million years based on models of jet propagation and lobe expansion. This timescale exceeds the typical duration of radio galaxy activity inferred from statistical studies of radio galaxy populations. Most radio sources appear to remain active for tens of millions of years before the central black hole exhausts its fuel supply or the accretion rate drops below the threshold needed to sustain jet production. The existence of Alcyonius implies either that its central black hole has maintained an unusually steady supply of infalling matter over an extended period, or that the jets have propagated exceptionally efficiently through an unusually low-density environment, or both. The lack of nearby galaxies or dense gas clouds in Alcyonius's vicinity supports the low-density hypothesis, but this alone doesn't fully explain the extreme size. The intergalactic medium itself deserves examination. The space between galaxies isn't truly empty. It contains gas at extremely low densities, typically between 10 to the -7 and 10 to the -5 particles per cubic centimetre. This represents a far better vacuum than anything achievable in terrestrial laboratories, yet over cosmic distances this tenuous gas exerts significant influence on structures passing through it. The gas consists primarily of ionised hydrogen, with trace amounts of heavier elements, heated to temperatures ranging from 10,000 to 10 million degrees, depending on location and history. In regions near galaxy clusters, the intracluster medium can be much denser, reaching 10 to the -3 particles per cubic centimetre, and temperatures of 100 million degrees. Radio jets propagating through such environments encounter substantial resistance, limiting their growth. Alcyonius's location away from dense clusters likely contributed to its extreme size by providing a path of least resistance. The lobes themselves contain magnetic fields with strengths measured in microgauss, roughly 1/1,000,000th the strength of Earth's magnetic field. Despite their weakness by terrestrial standards, these fields play a crucial role in containing and shaping the lobes. The magnetic pressure, the energy density stored in the magnetic field, helps inflate the lobes against the thermal pressure of the surrounding intergalactic medium. Without magnetic fields, the hot plasma in the lobes would dissipate rapidly. The fields also determine how efficiently particles radiate away their energy. Electrons spiraling in stronger magnetic fields radiate more intensely and lose energy faster, while those in weaker fields maintain their energy longer and produce fainter but more extended emission. The faint, diffuse nature of Alcyonius' outer lobes indicates that the magnetic fields there have weakened as the lobes expanded, and the electron population has aged considerably since being injected by the jets. Spectral aging analysis provides another tool for estimating lobe ages. When fresh particles enter the lobes through the jets, they possess a distribution of energies that produces synchrotron radiation across a broad range of frequencies. As time passes, the highest energy particles radiate away their energy most quickly, causing the spectrum to steepen. The ratio of low frequency to high frequency emission therefore encodes information about particle age. Applying this technique to Alcyonius's lobes yields age estimates consistent with the hundreds of millions of years inferred from propagation models, though uncertainties in the initial particle energy distribution and the magnetic field history introduce significant error bars. The outer regions of the lobes show steeper spectra than the inner regions, confirming that the emission there originates from an older particle population that has had more time to lose energy. The question of what determines maximum lobe size has no simple answer. Several factors potentially limit how large radio lobes can grow. First, the jets may simply turn off when the central black hole exhausts its fuel supply or transitions to a different accretion mode that doesn't produce jets. Without continuous injection of fresh particles and energy, the lobes would cease expanding and begin to fade as their particle populations age beyond detectability. Second, the intergalactic medium may become dense enough at some distance from the host galaxy that the jets can no longer overcome the ram pressure resistance. The jets would stall, creating lobes that reach a maximum size determined by the balance between jet power and environmental density. Third, buoyancy effects might cause the lobes to rise out of the galactic plane, lifting them into regions where they become detached from the jets and drift away as independent bubbles of magnetized plasma. Alcyonius shows no clear signs of having reached any of these limits. The hotspots at the ends of the lobes remain visible in radio observations, indicating that the jets continue to deliver energy to these regions. The lobes don't display the highly distorted morphology that would suggest strong environmental interactions or buoyant rise. The structures maintain their axis alignment with the host galaxy, consistent with ongoing jet activity rather than passive aging. This suggests that Alcyonius may still be growing, its lobes continuing to expand into intergalactic space even as we observe them. If the jets remain active for another 100 million years, the lobes could extend to 20 million light-years or beyond, assuming they encounter no significant obstacles. Other giant radio galaxies provide comparative context. The previous record holder, also discovered through LOFAR observations, extended roughly 12.6 million light-years. Before that, giants like 3C236 and J1420-0545 held attention with lobes spanning approximately 15 and 12 million light-years respectively, though measurement uncertainties made exact rankings difficult. These objects share certain characteristics with Alcyonius. They reside in relatively sparse environments, away from the dense cores of galaxy clusters. Their host galaxies tend to be massive ellipticals with old stellar populations. The black holes powering them fall within the typical range for galaxies of their mass. No obvious physical parameter separates them from the much larger population of smaller radio galaxies. The distinction appears to lie not in the galaxies themselves, but in their circumstances, their locations and their histories. Statistical studies of giant radio galaxy populations reveal that they occur preferentially in underdense regions of the cosmic web. The cosmic web describes the large-scale structure of the universe, the network of filaments, sheets, and voids that matter organizes itself into under the influence of gravity. Galaxies cluster along filaments and at the intersections of filaments called nodes. Between the filaments lie vast voids, regions with substantially below average galaxy densities. Giant radio galaxies appear more frequently in these underdense regions than in dense clusters, supporting the hypothesis that low environmental density enables extreme lobe growth. However, this correlation isn't absolute. Some giant radio galaxies do exist in denser environments, and many galaxies in underdense regions produce only modest radio structures. Environmental density appears necessary but not sufficient to explain giant radio galaxy formation. The age of the radio source relative to the age of the galaxy also matters. Galaxies evolve over cosmic time, their black holes growing through accretion and mergers, their gas reservoirs depleting through star formation and feedback processes. Young galaxies with abundant gas supplies might fuel intense but brief periods of radioactivity, producing bright but compact sources. Older galaxies with depleted gas reservoirs might sustain weaker but longer-lived jets, allowing lobes to grow larger despite lower instantaneous jet power. Alcyonius, with its old stellar population and lack of ongoing star formation, fits this pattern. Its central black hole likely finished its main growth phase billions of years ago and now accretes at a relatively modest rate. Drawing on residual gas in the galactic halo or material captured from the intergalactic medium. This slow, steady accretion could maintain jet activity over the extended timescales needed to build structures of this scale. Merger history also plays a role. When two galaxies merge, their central black holes eventually sink to the center of the merged system through dynamical friction. During this process, gas gets funneled toward the black holes, potentially triggering intense accretion and powerful jet activity. However, mergers also disturb the galactic environment, potentially misaligning the black hole spin axis with the accretion disk and disrupting stable jet production. The cleanest, most symmetric radio sources tend to come from galaxies that haven't experienced recent major mergers, allowing their black holes to establish stable accretion geometries. Alcyonius's regular morphology suggests it hasn't undergone a major merger in the time period during which its lobes have been growing. Any earlier merger history has been erased by billions of years of subsequent evolution. The duty cycle of radio galaxy activity introduces additional complexity. Many galaxies show evidence of multiple episodes of radioactivity separated by periods of quiescence. These galaxies display multiple pairs of lobes, older faded structures surrounding younger, brighter ones. Each episode represents a phase when the central black hole accreted sufficient matter to power jets, followed by a phase when accretion dropped below the threshold for jet production. Alcyonius appears to be in its first major radio phase, or at least shows no clear evidence of earlier episodes. This suggests that its central black hole has sustained the current episode of jet activity for the entire time needed to build the observed lobes without significant interruptions. Maintaining such consistency over hundreds of millions of years requires remarkable stability in the accretion process. Theoretical models of jet propagation have grown increasingly sophisticated as computational power has increased. Early analytical models treated jets as simple cylinders pushing through a uniform medium. Modern simulations incorporate three-dimensional magnetohydrodynamics, following the evolution of magnetic fields, shockwaves, and turbulence as jets interact with realistic intergalactic environments. These simulations reveal that jet propagation is far from smooth. The jets develop instabilities that cause them to wiggle and flare. They encounter density variations in the intergalactic medium that deflect them or cause them to temporarily brighten or dim. The bow shock at the jet terminus, where the jet collides with previously undisturbed gas, develops complex structure, including reflected shocks that propagate back along the jet. Despite these complications, the simulations confirm that jets can indeed propagate for millions of light years under the right conditions, validating the basic picture while adding layers of detail that observations are only beginning to resolve. Magnetic field amplification at the jet terminus represents one of the critical processes these simulations reveal. When a relativistic jet slams into the intergalactic medium, it creates a shocked region where gas compresses and heats to extreme temperatures. In this turbulent environment, small-scale magnetic fields get stretched and twisted, amplifying them through dynamo processes. The amplified fields can reach strengths hundreds or thousands of times greater than the ambient intergalactic magnetic field. These enhanced fields play a crucial role in accelerating particles to the high energies needed to produce the observed radio emission. The particles gain energy through a process called diffusive shock acceleration, repeatedly crossing back and forth through the shock front and receiving an energy boost with each crossing. Over time, this mechanism builds up a population of ultra-relativistic electrons that spiral in the magnetic fields and generate the synchrotron radiation we detect. The energy budget of Alcyone staggers the imagination. To maintain jets capable of inflating lobes 16 million light-years across requires a sustained power output of roughly 10 to the 42 ergs per second, equivalent to converting approximately 1/10 of a solar mass into pure energy every year. Over the estimated lifetime of the lobes, this amounts to tens of millions of solar masses worth of energy released into intergalactic space. Not all of this energy goes into the lobes themselves. Much of it heats the surrounding intergalactic medium, driving it away from the galaxy and creating a cavity in the cosmic web. The lobes also do work against the pressure of the intergalactic medium as they expand, converting jet energy into the kinetic energy of displaced gas. Only the fraction that goes into accelerating particles and amplifying magnetic fields contributes to the radio emission we observe, typically around 1% of the total jet power. The source of this energy ultimately traces back to gravitational potential energy released as matter falls toward the black hole. A non-rotating black hole can convert at most 6% of infalling mass into energy through accretion. A maximally spinning black hole can reach 42% efficiency if the Blandford-Znajek mechanism operates optimally. These numbers represent theoretical maxima. Real accretion systems achieve lower efficiencies due to various losses and inefficiencies in converting gravitational energy to jet power. Even accounting for these reductions, the total mass that must have accreted onto Alcyone's central black hole over the lifetime of its jets likely amounts to hundreds of millions of solar masses, a substantial fraction of the black hole's current mass. This raises questions about where all that matter came from and how it reached the black hole at a steady enough rate to maintain consistent jet activity. Gas reservoirs in massive elliptical galaxies provide one source. Despite having ceased active star formation, these galaxies retain hot gaseous halos with masses comparable to or exceeding their stellar masses. This gas sits in approximate hydrostatic equilibrium, supported against collapse by its thermal pressure. However, cooling processes slowly rob the gas of energy, particularly in the inner regions where densities are higher. As gas cools, it loses pressure support and begins to fall inward, potentially feeding the central black hole. This process, called cooling flow, can supply accretion rates of several solar masses per year in massive ellipticals, sufficient to power moderate jets over extended periods. The jets themselves may regulate this process through feedback, heating the gas and preventing it from cooling too quickly, establishing a self-regulating cycle that maintains both the hot halo and the black hole accretion rate. The intergalactic medium itself offers another potential fuel source. As a galaxy moves through intergalactic space, it plows through the diffuse gas filling the cosmic web. This gas can be captured by the galaxy's gravitational potential and eventually funnel toward the center. The effectiveness of this mechanism depends on the galaxy's velocity relative to the intergalactic medium and the density of that medium. For a galaxy moving at typical velocities of a few hundred kilometers per second through gas at densities of 10 to the -5 particles per cubic centimeter, the capture rate amounts to perhaps a fraction of a solar mass per year, not enough by itself to power jets like those of Alcyonius, but potentially contributing to the overall accretion budget. Over hundreds of millions of years, even modest accretion rates accumulate to significant masses. Galaxy interactions and minor mergers provide episodic fuel deliveries. Even though Alcyonius shows no signs of major recent mergers, it likely experienced numerous minor mergers over its history, absorbing smaller satellite galaxies that wandered too close. Each such event delivers gas to the central regions, potentially triggering or enhancing accretion onto the black hole. If these minor mergers occurred at a sufficient rate, they could explain the sustained accretion needed to maintain jet activity. The timing would need to be fortunate, with mergers occurring frequently enough to prevent the accretion rate from dropping too low, but not so violently as to disrupt the stable jet geometry. This delicate balance might explain why giant radio galaxies remain relatively rare despite the ubiquity of minor mergers. The orientation of Alcyonius, relative to our line of sight, affects what we observe. Radio galaxies viewed from different angles display different apparent characteristics. When we look nearly along the jet axis, we see a blazar, a compact bright source dominated by Doppler-boosted emission from the jet pointing toward us. When we view perpendicular to the jet axis, we see the classical double-lobed morphology, with the host galaxy visible between the lobes. Alcyonius appears to be oriented close to perpendicular to our line of sight, based on the symmetry of its lobes and the absence of strong core emission. This orientation allows us to appreciate the full extent of the structure, but it also means that the jets appear fainter than they would if oriented toward us. The true energy output of the jets must be calculated by correcting for this orientation, though uncertainties in the exact viewing angle introduce corresponding uncertainties in derived jet powers. Redshift effects further complicate observations. Alcyonius lies at a redshift of 0.247, meaning the light we receive left the galaxy roughly 3 billion years ago. The universe has expanded by approximately 25% since that light began its journey, stretching wavelengths and diluting photon energies. Radio observations must account for these cosmological effects when measuring source properties. The observed radio frequency corresponds to a higher rest frame frequency in the source. The observed angular size must be converted to physical size using cosmological models that account for the universe's expansion history. Uncertainties in cosmological parameters, particularly the dark energy density and the Hubble constant, translate into uncertainties in derived distances and sizes, though for objects at Alcyonius's redshift these uncertainties amount to only a few percent. The discovery of Alcyonius through LOFAR data highlights how technological advances continue to reshape our census of cosmic structures. Radio astronomy has progressed through several generations of instruments, each opening new observational windows. Early radio telescopes consisted of single large dishes, limited in sensitivity and resolution by their physical size. Interferometry revolutionized the field by combining signals from multiple telescopes to synthesize apertures far larger than any single dish could achieve. The Very Large Array in New Mexico, completed in 1980, demonstrated the power of this approach with its 27-dish configuration, spanning 36 kilometers. The technique achieved angular resolutions rivaling optical telescopes, while operating at radio wavelengths where atmospheric distortion poses minimal problems. LOFAR represents the next step in this evolution. Instead of large movable dishes, it employs thousands of simple dipole antennas distributed across Europe. These antennas operate at frequencies between 10 and 240 MHz, the low end of the radio spectrum typically avoided by other facilities due to interference from terrestrial sources and ionospheric effects. However, this frequency range proves ideal for studying aged synchrotron emission from extended radio sources. The low frequencies penetrate through intervening material more effectively than higher frequencies, and remain sensitive to the faint diffuse emission from distant lobes that have been expanding for hundreds of millions of years. The distributed nature of LOFAR's antenna stations provides sensitivity to structures on multiple angular scales simultaneously, from compact cores to extended lobes spanning degrees on the sky. Data processing for LOFAR observations requires substantial computational resources. The system generates data at rates exceeding terabits per second, as signals from thousands of antennas are digitized and correlated. Sophisticated calibration algorithms correct for ionospheric disturbances, antenna beam patterns, and radio frequency interference from terrestrial sources. The raw data must be transformed through Fourier analysis to create images of the sky, a process that becomes increasingly computationally demanding as the number of antennas and the bandwidth increase. A single deep LOFAR observation can require weeks of processing time on dedicated computing clusters to produce final calibrated images. The effort proves worthwhile when these images reveal structures invisible to all previous surveys. The systematic search that uncovered Alcyonius examined LOFAR data, covering several thousand square degrees of sky. Researchers developed automated algorithms to identify extended radio sources and measure their angular sizes. The challenge lies in distinguishing genuinely large structures from multiple unrelated sources that happen to lie along the same line of sight. Visual inspection remains necessary to confirm candidate giant radio galaxies, examining whether the morphology displays the characteristic symmetry of radio lobes and whether the emission connects smoothly back to a central host galaxy. Alcyonius emerged from this process as an immediately obvious outlier, its lobes extending far beyond any previously catalogued source in the survey region. Confirmation of the discovery required cross-referencing with optical and infrared surveys to identify the host galaxy and measure its redshift. The Sloan Digital Sky Survey provided the optical identification, revealing the massive elliptical galaxy at the position midway between the radio lobes. Spectroscopic observations from the SDSS archive confirmed the redshift and measured the properties of the stellar population. No previous radio surveys had flagged this galaxy as particularly noteworthy. Higher frequency radio catalogues showed only a modest compact source at the galaxy's position, completely missing the extended lobes that dominate the low-frequency emission. This illustrates how selection effects shape our understanding of the radio galaxy population. Surveys optimized for finding compact bright sources systematically miss the largest and most diffuse structures. The spatial distribution of giant radio galaxies across the sky provides clues about their relationship to large-scale structure. If these objects require special environmental conditions, they should cluster in regions where those conditions prevail. Early studies suggested that giant radio galaxies avoid rich galaxy clusters, consistent with the hypothesis that low-density environments enable lobe growth. However, as samples have grown with improved surveys, the picture has become more nuanced. While giant radio galaxies do show preference for underdense regions, they don't exclusively occupy voids. Some reside in moderate density environments, suggesting that factors beyond simple density play roles in determining final sizes. The relationship between giant radio galaxies and the cosmic web warrants further investigation with larger statistical samples. Alcyonius's specific location within the cosmic web has been mapped using galaxy surveys that trace the three-dimensional distribution of matter in its neighbourhood. The analysis reveals that it sits in a filament of the cosmic web, not in a dense cluster node, but also not in a true void. The filament provides a moderate density environment, lower than cluster cores but higher than the most underdense regions of space. This intermediate environment may actually be optimal for giant radio galaxy formation, providing enough matter to fuel sustained accretion while remaining diffuse enough to allow unimpeded lobe expansion. The filament's orientation relative to the radio jets shows no obvious correlation, suggesting that large-scale tidal fields don't significantly influence jet direction on the scales relevant to individual galaxies. Comparison with simulations of structure formation adds theoretical context. Modern cosmological simulations follow the evolution of dark matter and baryonic matter from early universe density fluctuations through billions of years of gravitational collapse and hierarchical structure assembly. These simulations reproduce the observed cosmic web and predict the properties of the intergalactic medium in different environments. Jets propagating through simulated intergalactic medium show behaviour consistent with observed giant radio galaxies, reaching similar sizes when environmental conditions match those inferred for systems like Alcyonius. The simulations also predict that the largest radio galaxies should preferentially align with cosmic web filaments, though observational tests of this prediction remain inconclusive due to limited sample sizes and measurement uncertainties. The impact of radio galaxy jets on their surroundings extends beyond simple displacement of gas. The energy deposited by jets heats the intergalactic medium, raising its temperature and reducing its density over volumes far larger than the visible radio lobes. This heating can suppress star formation in nearby galaxies by preventing cold gas from accumulating. It can also affect the subsequent evolution of the host galaxy itself by establishing a feedback loop where jet heating prevents gas from cooling onto the central black hole, regulating the accretion rate and potentially causing the jets to cycle on and off over cosmic time. For a system as large as Alcyonius, the sphere of influence where jet heating significantly affects the thermal state of the intergalactic medium could extend beyond 20 million light-years, encompassing hundreds of neighbouring galaxies. Observational evidence for this widespread heating remains indirect but suggestive. Studies of the intergalactic medium in regions surrounding giant radio galaxies reveal systematically higher temperatures and lower densities compared to control regions at similar distances from galaxies without active radio sources. The excess heating correlates with the integrated energy output of the jets, supporting the picture that radio galaxies fundamentally alter their cosmic neighbourhoods. For Alcyonius specifically, the energy injected into intergalactic space over hundreds of millions of years equals roughly 10 to the 60 ergs, enough to raise the temperature of gas within a sphere 30 million light-years in radius by millions of degrees. This heating doesn't occur uniformly, but concentrates along the jet axis where energy deposition is most direct, creating elongated, heated regions that can persist for billions of years after the jets shut off. The magnetic fields carried by the jets also permanently magnetize the intergalactic medium. Before a radio galaxy activates, the magnetic field in intergalactic space is extraordinarily weak, perhaps a billionth the strength of Earth's magnetic field, generated primarily through primordial mechanisms or by outflows from earlier generations of galaxies. Radio jets increase field strengths by factors of thousands within their lobes, and by factors of tens to hundreds in surrounding regions where turbulence generated by the expanding lobes amplifies seed fields. These enhanced magnetic fields affect subsequent structure formation by providing additional pressure support and by influencing how cosmic rays propagate through intergalactic space. Over cosmic time, the cumulative effect of billions of radio galaxies may have magnetized substantial fractions of the cosmic web, establishing a magnetized universe on the largest scales. Cosmic ray acceleration in radio galaxy lobes contributes to the population of high-energy particles pervading intergalactic space. The same shock acceleration processes that energize electrons to produce synchrotron radiation also accelerate protons and heavier nuclei. These cosmic ray particles can reach energies far exceeding anything achievable in terrestrial accelerators, potentially extending to ultra-high energy cosmic rays with energies above 10 to the 18th electron volts. While the exact contribution of radio galaxies to the ultra-high energy cosmic ray spectrum remains debated, circumstantial evidence supports a connection. The arrival directions of the highest energy cosmic rays show slight correlations with the positions of nearby active galactic nuclei, and the total energy requirements match what radio galaxies could plausibly supply. Alcyonius, with its enormous lobes and sustained jet activity, likely injects substantial numbers of cosmic ray particles into intergalactic space, particles that will eventually propagate throughout the local universe. The fate of Alcyonius's lobes once the jets eventually shut off presents another area of theoretical investigation. Without continuous energy input from the jets, the lobes will begin to fade as their electron populations age beyond detectability. The timescale for this fading depends on the magnetic field strength and the initial electron energy distribution. Estimates suggest that lobes like those of Alcyonius could remain detectable for several 100 million years after jet activity ceases, though they would become progressively fainter and more difficult to observe. Eventually the lobes will fade below detection thresholds, leaving behind only their thermal and magnetic imprints on the intergalactic medium. These ghost cavities, regions of lower density and higher temperature with enhanced magnetic fields, can persist for billions of years as relics of past radio galaxy activity. Searches for these relic lobes have intensified as low-frequency radio surveys become more sensitive. Relic lobes lack the hotspots and compact features associated with active sources. Their radio spectra show extreme steepness, with emission dropping off rapidly at higher frequencies. LOFAR's sensitivity to steep spectrum sources makes it ideal for detecting relics. Several candidates have been identified, displaying the expected morphological and spectral properties. If confirmed, these relics would demonstrate that the current census of giant radio galaxies represents only the presently active systems, with a much larger population of extinct giants lurking in deep low-frequency surveys. Alcyoneus itself will someday join this population, its lobes fading into the background as its central black hole exhausts its fuel supply. The question of whether even larger radio galaxies exist remains open. Alcyoneus's discovery demonstrates that previous size limits reflected observational constraints rather than physical boundaries. LOFAR has now surveyed only a fraction of the sky at the depth and resolution needed to detect sources like Alcyoneus. As the survey continues and data processing techniques improve, larger giants may emerge. Theoretical models place no firm upper limit on radio lobe size. Jets could potentially propagate tens of millions of light-years if environmental conditions permitted and if fuel supplies sustained them long enough. The practical limit likely comes from the finite density of even the most underdense regions of space and the eventual exhaustion of accreting matter, but exactly where that limit lies remains uncertain. Alternative hypotheses suggest that Alcyoneus may not represent the extreme tail of a continuous size distribution, but rather a distinct class of object. Perhaps giant radio galaxies exceeding 10 million light-years require a qualitatively different formation mechanism than their smaller cousins. This could involve black hole spins aligned in particularly favourable orientations, or accretion geometries that maximize jet efficiency, or environmental configurations that provide unusually straight paths through intergalactic space. Testing these hypotheses requires larger samples of giant radio galaxies with well-characterized properties, allowing statistical comparisons between giants and normal-sized sources. Current samples remain too small to definitively distinguish between competing explanations. The relationship between radio galaxy size and cosmic epoch adds another dimension to consider. The universe evolves over time, with galaxy formation rates, merger rates, and gas densities all changing as the cosmos ages. The intergalactic medium becomes more rarefied as the universe expands, potentially making it easier for jets to propagate to extreme distances in the present day compared to earlier epochs. Conversely, fuel supplies for black hole accretion were more abundant in the past when galaxies contained more gas, potentially enabling more powerful jets despite denser environments. Observational studies comparing giant radio galaxy properties across different redshifts could reveal whether these objects become more or less common as we look back in cosmic time, constraining models of their formation. Current surveys show tentative evidence that the largest radio galaxies occur preferentially at moderate redshifts, between roughly 0.2 and 0.7, corresponding to look-back times of 2 to 6 billion years. This epoch represents a transition period in cosmic history, when the universe had evolved beyond its peak era of star formation and galaxy mergers, but before the intergalactic medium had been diluted too severely by expansion. The combination of still reasonably dense environments, abundant fuel from recent galaxy interactions, and mature black holes that had settled into stable configurations may create optimal conditions for giant radio galaxy formation. Alcyoneus, at redshift 0.247, sits squarely within this favoured epoch, consistent with the hypothesis that cosmic conditions at this particular time prove most conducive to extreme lobe growth. However, selection effects complicate this interpretation. Giant radio galaxies at higher redshifts become increasingly difficult to detect as cosmological dimming reduces their apparent brightness, and as their emission shifts to lower observed frequencies where atmospheric and ionospheric effects degrade data quality. Current surveys may simply lack the sensitivity to detect counterparts to Alcyoneus at redshifts beyond 1, even if such objects exist in comparable numbers. Next-generation radio telescopes, particularly the Square Kilometre Array currently under construction, will provide the sensitivity needed to detect giant radio galaxies across a broader range of cosmic epochs, definitively testing whether the apparent concentration at moderate redshifts reflects real physics or observational bias. The internal structure of Alcyoneus's lobes encodes additional information about jet evolution and environmental interactions. High-resolution radio imaging reveals that the lobes are not uniform clouds of emission, but contain filamentary structure, bright ridges and lanes of enhanced emission interleaved with fainter regions. This structure likely traces variations in magnetic field strength and particle density created by instabilities in the expanding lobes. Kelvin-Helmholtz instabilities, develop along the interface between the lobe plasma and the surrounding intergalactic medium, generating turbulence that mixes the two fluids and creates the observed filamentary patterns. Rayleigh-Taylor instabilities may also contribute, particularly if the lobe plasma is buoyantly rising relative to the denser external gas. Spectral index mapping, which measures how emission intensity varies with frequency across the source, reveals systematic gradients within the lobes. The spectrum is flattest near the jets and hotspots where fresh particles are being injected, and steepest in the outer regions and in areas far from the jets where particles have aged longest. These gradients allow reconstruction of the history of particle injection and energy loss, providing insights into how jet power has varied over time. In Alcyonius, the relatively uniform spectral index across most of the lobes suggests that jet power has remained fairly constant throughout the lobe's growth, without dramatic episodes of increased or decreased activity. This consistency supports models in which giant radio galaxy formation requires sustained rather than episodic jet activity. Polarization measurements add yet another layer of information. Synchrotron radiation is intrinsically polarized, with the electric field vector perpendicular to the magnetic field direction. By measuring the polarization angle across a radio source, astronomers can map the magnetic field structure. Alcyonius displays ordered polarization patterns consistent with magnetic fields aligned predominantly along the jet direction near the core and becoming more tangled and random in the outer lobes. The degree of polarization, the fraction of emission that is polarized, decreases from roughly 30% near the hotspots to 10% or less in the diffuse lobe material, indicating increasing magnetic field disorder as the plasma ages and turbulent processes scramble the original field geometry. Faraday rotation complicates polarization measurements, but also provides useful diagnostic information. As polarized radio waves propagate through magnetized plasma, their polarization angle rotates by an amount proportional to the square of the wavelength and to the integrated electron density and magnetic field strength along the line of sight. This rotation measure can be measured by observing at multiple frequencies and tracking how the polarization angle changes. For Alcyonius, rotation measures are small in most of the lobes, indicating that the line of sight through the lobe plasma and foreground intergalactic medium contains relatively little magnetized material. However, near the host galaxy where densities are higher, rotation measures increase, providing constraints on the magnetic field strength in the galactic halo. The jets themselves remain partially unresolved even in the highest resolution observations currently available. While the lobes extend clearly across millions of light years, the narrow channels connecting them to the galactic core often appear as thin filaments, or even gaps in the emission where sensitivity falls below detection thresholds. This doesn't mean the jets aren't there. It means that the jets contain too few particles radiating at detectable levels to stand out clearly above the noise. The jets likely remain highly collimated, with widths of only thousands of light years even at distances of millions of light years from the core. Maintaining such collimation over these distances requires that the magnetic field structure in the jets remains remarkably stable, neither dissipating through turbulent diffusion nor being disrupted by interactions with the external medium. Theoretical models of jet collimation invoke various mechanisms. Magnetic hoop stress, the self-constricting force generated by azimuthal magnetic fields threading through the jet, can pinch the jet and prevent it from expanding. External pressure from the surrounding medium can also confine jets, though this mechanism becomes less effective at large distances where environmental pressures drop. Some models propose that jets remain collimated through continuous magnetic field generation along their length, with dynamo processes in the jet shear layer constantly replenishing the confining fields. The jets of Alcyonius appear straight to within measurement uncertainties over their entire visible length, suggesting that whatever collimation mechanism operates does so with high efficiency. Precession of the jet axis represents another phenomenon that can affect radio galaxy morphology. If the accretion disk surrounding the black hole is misaligned with the black hole spin axis, lens-thirring precession will cause the disk to wobble, dragging the jet base with it. This creates radio sources with bent or twisted morphologies, sometimes displaying S-shaped or helical patterns. Alcyonius shows no obvious signs of precession, implying that its black hole spin axis and accretion disk are well aligned. The timescale for this alignment to establish itself depends on the mass and angular momentum of the accreting material and can range from thousands to millions of years. The absence of precession signatures suggests that Alcyonius has maintained a stable accretion geometry throughout the period of lobe growth. Environmental asymmetries potentially explain minor differences between the two lobes of Alcyonius. While the lobes appear nearly symmetric at low resolution, detailed measurements reveal that one lobe extends slightly further than the other and displays somewhat brighter emission. These asymmetries could arise from density gradients in the intergalactic medium, with the longer lobe propagating through a region of lower density that offers less resistance to jet advance. Alternatively, the asymmetries might reflect intrinsic variations in jet power, with the jets not being perfectly balanced in their energy output to either side. Distinguishing between these possibilities requires independent measurements of the intergalactic medium density distribution, which remain challenging given the extremely low densities involved. The velocity of the host galaxy relative to the intergalactic medium introduces another potential source of asymmetry. A galaxy moving through intergalactic space experiences a ram pressure wind from the oncoming gas, similar to how a moving car experiences wind resistance. This ram pressure can deflect radio jets, causing them to trail behind the galaxy's motion. For typical galaxy velocities of a few hundred kilometers per second and typical intergalactic medium densities, the deflection angle amounts to several degrees over distances of millions of light-years. Alcyonius's jets show no strong evidence of such deflection, suggesting either that the galaxy's peculiar velocity is small or that it moves primarily perpendicular to our line of sight, making any deflection difficult to detect in projection. Future proper motion measurements, tracking the galaxy's motion across the sky over years or decades, could resolve this ambiguity. The total mass contained within Alcyonius's lobes can be estimated from their volume and the inferred particle density. The lobes span roughly 16 million light-years in length, with widths of approximately 1 to 2 million light-years, giving a total volume on the order of 10 to the 69 cubic centimeters. Particle densities in the lobes likely range from 10 to the -4 to 10 to the -3 particles per cubic centimeter based on spectral modelling, in comparison with other radio galaxies. These values imply total particle masses of roughly 10 million to 100 million solar masses distributed across the lobes. This represents a small fraction of the total mass that has accreted onto the central black hole, with most of the accreted mass contributing to the black hole's growth and to powering the jets rather than ending up in the lobes themselves. The momentum carried by the jets also warrants consideration. Relativistic jets transport not just energy but also momentum, and when they terminate in the hotspots, this momentum gets transferred to the intergalactic medium. The momentum flux can be estimated from the jet power and the bulk velocity of the jet material. For Alcyonius, the estimated momentum deposition rate amounts to roughly 10 to the 39 gram centimeters per second per year, sustained over hundreds of millions of years. This accumulated momentum has displaced enormous volumes of intergalactic gas, pushing it outward from the jet axis and creating the low density cavities occupied by the lobes. The kinetic energy of this displaced gas, though typically only a few % of the total jet energy, still amounts to 10 to the 59 ergs, equivalent to thousands of supernova explosions. Chemical enrichment by the jets provides another avenue for their lasting impact. While jets consist primarily of electrons and protons, they also contain small amounts of heavier elements synthesized in the stars of the host galaxy and expelled by supernova explosions and stellar winds. These heavy elements, mostly carbon, nitrogen, oxygen and iron, get incorporated into the gas flowing toward the central black hole and then carried outward by the jets. The total mass of heavy elements deposited into the intergalactic medium by Alcyonius's jets over their lifetime likely amounts to hundreds of thousands to millions of solar masses. This enriched material mixes with the pristine intergalactic gas, raising its metallicity and affecting the properties of any stars that eventually form from this gas in future generations of galaxies. The evolution of metallicity in the intergalactic medium over cosmic time reflects the cumulative effect of all such enrichment processes. Early in cosmic history, the intergalactic medium contained only hydrogen and helium from the Big Bang. As stars formed, burned, and died, they produced heavier elements that winds and explosions ejected into intergalactic space. Active galactic nuclei and radio galaxies accelerated this mixing, transporting enriched gas from galactic centers to the cosmic web beyond. modern measurements show that even the most underdense regions of intergalactic space contain detectable amounts of heavy elements, about 10% of solar abundances in well-studied regions. Giant radio galaxies like Alcyonius contribute disproportionately to this enrichment due to their ability to transport material across unprecedented distances. Alcyonius's relationship to the broader active galactic nucleus population raises questions about evolutionary sequences. Do all radio galaxies pass through a giant phase if given sufficient time and favourable conditions? Or do giants represent a separate branch requiring special initial conditions? Statistical studies comparing the properties of giant and normal radio galaxies show more similarities than differences. The host galaxy masses, black hole masses, and accretion rates span similar ranges. The primary distinction lies in the environmental properties, with giants preferentially occupying less dense regions. This suggests that most radio galaxies could potentially become giants given appropriate circumstances rather than requiring fundamentally different formation pathways. The accretion mode of the central black hole influences jet properties in ways that affect ultimate lobe size. Black holes can accrete in two primary modes: a radiatively efficient mode where the accretion disk is geometrically thin and optically thick, converting gravitational energy efficiently into radiation, and a radiatively inefficient mode where the accretion flow is geometrically thick and optically thin, with much of the energy advecting into the black hole rather than being radiated. The radiatively inefficient mode, often called an advection-dominated accretion flow, tends to produce more powerful jets relative to the accretion rate. Alcyonius likely operates in this mode given its modest optical and X-ray luminosity compared to its radio power, consistent with most radio galaxies in the local universe. The transition between accretion modes depends critically on the accretion rate relative to the Eddington limit, the maximum rate at which a black hole can accrete while remaining in hydrostatic equilibrium. At high accretion rates exceeding a few percent of Eddington, the thin disk mode dominates, producing bright quasars with relatively weak jets. Below a few percent of Eddington, the flow transitions to the geometrically thick radiatively inefficient mode, reducing radiative output but enhancing jet production. Alcyonius's central black hole appears to be accreting at roughly 1% of its Eddington limit based on estimates of its mass and luminosity, placing it squarely in the regime where efficient jet production occurs. This accretion rate, while modest compared to luminous quasars, proves sufficient to power the observed jets when sustained over hundreds of millions of years. The feedback loop between jet activity and accretion rate may explain the longevity of Alcyonius's jets. As the jets heat the surrounding gas, they reduce the rate at which material can cool and accrete onto the black hole. This creates a self-regulating system where increased accretion leads to stronger jets, which heat more gas, which reduces accretion, which weakens the jets, allowing gas to cool again and resume accretion. This cycle can stabilize at a quasi-steady state, where accretion rates fluctuate around an average value determined by the balance between heating and cooling. For Alcyonius, this balance appears to have been maintained at a level that sustains jet activity over timescales far longer than typical for radio galaxies, either because the initial gas reservoir was particularly large or because the feedback operates with unusual efficiency. The cosmic microwave background provides an additional energy source for the lobe electrons through inverse Compton scattering. Cosmic microwave background photons pervade all of space, remnants of the Big Bang now cooled to a temperature of roughly 3 degrees above absolute zero. When relativistic electrons in radio galaxy lobes collide with these photons, they can boost them to much higher energies, creating X-ray and gamma-ray emission. The efficiency of this process depends on the electron energies and the magnetic field strength. In low magnetic field environments, inverse Compton losses can dominate over synchrotron losses, causing electrons to radiate their energy as high-energy photons rather than radio waves. For Alcyonius, the magnetic field appears strong enough that synchrotron emission dominates, but inverse Compton processes still contribute to the overall energy budget and could potentially be detected by sensitive X-ray telescopes. Searches for X-ray emission from giant radio galaxies have produced mixed results. Some show clear detections consistent with inverse Compton emission, while others remain below detection limits. The detectability depends on the magnetic field strength, with weaker fields producing brighter X-ray emission for the same radio brightness. Alcyonius has not yet been observed with sufficient sensitivity to detect or rule out inverse Compton X-rays. Such observations would provide independent constraints on the magnetic field's strength and particle energy distribution, complementing the information available from radio data alone. The upcoming generation of X-ray telescopes may finally achieve the sensitivity needed to detect inverse Compton emission from distant giant radio galaxies. The number of giant radio galaxies in the observable universe likely exceeds current counts by orders of magnitude. LOFAR has surveyed only a few thousand square degrees of sky to the depth needed to detect objects like Alcyonius, representing less than 10% of the total sky area. If giant radio galaxies are distributed uniformly across the sky, current surveys have found only a small fraction of the total population. Extrapolating from detected numbers suggests tens of thousands of giant radio galaxies may exist within the survey volume accessible to LOFAR. Beyond this volume, at higher redshifts where cosmological dimming makes detection more challenging, millions more likely await discovery. Each represents a laboratory for studying extreme astrophysical processes and their impact on cosmic structure. The distribution of sizes among giant radio galaxies shows no obvious cutoff at 16 million light-years. The size distribution appears to follow a power law, with numbers decreasing steadily as size increases but without any sharp truncation. This suggests that Alcyonius, while currently the largest known, likely does not represent a fundamental physical limit. Larger galaxies probably exist but remain undetected due to their rarity and faintness. As surveys continue and detection methods improve, new record holders will likely emerge. The question is not whether larger galaxies exist, but rather how much larger they can grow before reaching true physical limits imposed by intergalactic medium density, fuel supplies, or jet lifetime. Theoretical extrapolations suggest that under optimal conditions, radio lobes could potentially extend beyond 30 million light-years before environmental resistance becomes insurmountable. This would require an exceptionally low-density environment, sustained jet activity for close to 1 billion years, and remarkable stability in both the jet production mechanism and the environmental conditions. Such extreme cases should be exceedingly rare, perhaps representing 1 in 1 million radio galaxies. Observing the entire sky to sufficient depth might uncover a handful of such objects, though distinguishing genuine 30 million light-year giants from projection effects where unrelated sources align would require careful analysis. The impact of such giants on cosmological observables deserves consideration. If radio galaxies can truly extend beyond 30 million light-years, they approach the scales relevant for cosmic microwave background studies and large-scale structure surveys. Radio lobes this large could potentially shadow or distort the cosmic microwave background through thermal and kinetic Sunyaev-Zeldovich effects, where the lobe plasma scatters cosmic microwave background photons and imprints spectral distortions. They could also affect measurements of the matter power spectrum by altering the distribution of baryons on large scales. Current cosmological analyses typically do not account for radio galaxy feedback on these enormous scales, but if giants substantially larger than Alcyonius exist in significant numbers, their cumulative effect might require consideration in precision cosmology. The lifetime of radio lobes introduces important timescales into models of galaxy evolution. Lobes that persist for hundreds of millions of years after jet activity ceases create long-lived reservoirs of energy and magnetized plasma that can affect subsequent generations of structure formation. A galaxy that produces multiple episodes of giant radio galaxy activity over its lifetime, separated by quiescent periods, could surround itself with concentric shells of relic lobes at various stages of fading. These shells would create a complex multi-phase intergalactic medium structure very different from the relatively uniform medium assumed in most galaxy formation models. Observations hint that such multi-episode giants may exist, though confirming their nature requires sensitive low-frequency observations capable of detecting extremely faint steep spectrum emission. The radiospectral energy distribution of Alcyonius extends from below 20 MHz to above 10 GHz, spanning more than 2 orders of magnitude in frequency. At the lowest frequencies, atmospheric absorption and ionospheric refraction limit ground-based observations, requiring space-based instruments or analysis of indirect effects. At the highest frequencies, the emission from the outer lobes becomes too faint to detect, as the aged electron population has radiated away most of its energy. The peak of the spectrum occurs around 100 MHz, firmly in LOFAR's observing band, explaining why this telescope proved so effective at revealing the full extent of the structure. Higher frequency surveys operating at 1 to 5 GHz detected only the inner brightest regions, missing the vast bulk of the lobe's volume. The spectral index, defined as the power law exponent describing how flux density varies with frequency, provides quantitative information about particle aging. Fresh particle populations injected near the hotspots display spectral indices around -0.5 to -0.7, meaning the flux density decreases modestly with increasing frequency. As particles age and lose energy, the spectrum steepens to indices of -1.5 or steeper in the oldest regions. Alcyonius shows spectral indices ranging from approximately -0.7 near the hotspots to -1.2 in the outer lobes, consistent with particle ages of several hundred million years in the most distant regions. This aging pattern confirms that the lobes have grown outward over time, with the oldest material farthest from the core. Models of spectral aging must account for several physical processes simultaneously. Synchrotron losses dominate at high particle energies, causing electrons to radiate their energy on timescales of millions to tens of millions of years, depending on magnetic field strength. Inverse Compton losses contribute additionally, particularly at the highest energies where the cosmic microwave background provides an efficient scattering target. Adiabatic expansion of the lobes also causes particles to lose energy, as they do work against the surrounding pressure. The relative importance of these processes varies with position within the lobes and with time as the magnetic field evolves. Sophisticated numerical models that simultaneously solve for particle transport, energy losses, and magnetic field evolution can reproduce the observed spectral patterns and constrain the physical parameters. Polarization properties evolve along with the spectrum as lobes age. Freshly accelerated particles in ordered magnetic fields produce highly polarized emission, with polarization fractions potentially exceeding 50%. As turbulence develops and magnetic fields become tangled, the polarization fraction decreases. Faraday depolarization, caused by field reversals along the line of sight through the lobe, further reduces observed polarization at lower frequencies. Alcyonius displays polarization fractions of 20 to 30% in the inner lobes, declining to below 10% in the outer regions, consistent with increasing magnetic field disorder as the lobes expand and age. The polarization angles align predominantly perpendicular to the jet direction in most regions, indicating that the magnetic field remains generally aligned with the jet despite the increasing disorder. The three-dimensional structure of the lobes remains uncertain due to projection effects. We observe Alcyonius projected onto the two-dimensional plane of the sky, unable to determine directly whether the lobes extend predominantly in the plane of the sky or have significant components along our line of sight. Theoretical models and statistical arguments suggest that lobes typically have aspect ratios of roughly 3 to 1, being longer along the jet axis than their width or depth. For Alcyonius, this would imply widths and depths of roughly 5 million light-years for lobes 16 million light-years long. However, individual sources can deviate substantially from average aspect ratios, and without independent distance indicators at multiple positions within the lobes, determining the true three-dimensional geometry remains challenging. Gravitational lensing by foreground structure could potentially magnify or distort the apparent size of Alcyonius, though this effect should be small for sources at moderate redshift. Light travelling from redshift 0.247 passes through the gravitational potential wells of intervening galaxies and clusters, which can deflect and focus the light. For extended sources like radiolobes, the differential magnification across the source creates distortions rather than simple magnification. Studies of gravitational lensing effects on radio galaxies show that typical magnifications amount to a few percent, with distortions becoming noticeable only when the source passes close to a massive foreground lens. No obvious massive structures lie along the line of sight to Alcyonius, suggesting that lensing corrections to its measured size should be minimal, likely below observational uncertainties. Cosmic variance in structure formation means that different regions of the universe develop differently, with some forming more massive structures earlier, while others remain relatively underdense. Alcyonius resides in a patch of universe that may be slightly underdense compared to the cosmic average, facilitating the growth of its enormous lobes. However, The universe is homogeneous on large scales, so significant deviations from average density occur only over limited volumes. If Alcyonius's size genuinely requires an unusually low-density environment, we would expect to find other giant radio galaxies clustering in the same general region of space. Surveys have not yet reached sufficient depth and completeness to test this prediction definitively, but future surveys should reveal whether giants cluster or distribute randomly. The dark matter distribution in Alcyonius's environment affects jet propagation indirectly through its gravitational influence on the baryonic component. Dark matter dominates the total mass budget, outweighing baryons by a factor of roughly 5 to 1. The dark matter forms the underlying gravitational potential wells in which baryons settle, determining the large-scale structure of the cosmic web. However, dark matter does not interact directly with the electromagnetic radiation comprising the jets. Its influence on jet propagation occurs only through the distribution and dynamics of the baryonic gas that provides the primary resistance to jet advance. Regions with more dark matter accumulate more baryonic gas, creating denser environments where jets struggle to propagate long distances. Alcyonius's location in a relatively underdense region likely corresponds to both lower dark matter and lower baryon densities. Simulations that include both dark matter and baryonic physics reproduce the formation of structures like giant radio galaxies, though predicting their exact properties requires substantial computational resources. Modern cosmological simulations follow billions of dark matter particles and baryonic fluid elements through cosmic history, resolving scales from tens of millions of light-years down to thousands of light-years. These simulations include prescriptions for star formation, supernova feedback, and black hole growth and feedback, though they typically lack the resolution to model jet physics in detail. Instead, jets are represented through subgrid models that approximate their energy and momentum injection. Despite these limitations, the simulations produce populations of simulated radio galaxies, with size distributions roughly matching observations, lending confidence to the theoretical framework. The energy spectrum of particles accelerated in Alcyonius's hotspots extends from thermal energies near a few thousand electron volts up to potentially ultra-relativistic energies exceeding 10 to the 15 electron volts. The acceleration mechanism operates most efficiently at a characteristic energy determined by the shock strength and magnetic field configuration, typically producing power law particle distributions where the number of particles decreases steadily with increasing energy. The exact form of this distribution affects both the radio emission properties and the overall energetics of the lobes. Steeper distributions concentrate more particles at lower energies, producing brighter low-frequency emission and longer synchrotron lifetimes. Flatter distributions extend to higher energies, creating emission that peaks at higher frequencies and particles that lose energy more rapidly through radiation. First-order Fermi acceleration, the dominant mechanism in strong shocks, naturally produces power law distributions with a universal slope determined only by the shock compression ratio. In the strong shock limit, where the downstream gas is compressed by a factor of 4 relative to the upstream gas, the theory predicts a particle energy distribution proportional to energy to the -2. Observations of radio galaxy hotspots generally confirm distributions close to this prediction, though variations occur due to energy-dependent escape of particles from the acceleration region and losses during acceleration. Alcyonius's hotspots display spectral indices consistent with particle distributions near the theoretical prediction, suggesting efficient shock acceleration operating under standard conditions. The maximum particle energy achievable in the hotspots depends on the balance between acceleration and loss rates. Particles gain energy through repeated shock crossings, but simultaneously lose energy through synchrotron radiation and adiabatic expansion. The maximum energy occurs where the acceleration timescale equals the loss timescale. For the conditions inferred in Alcyonius's hotspots, with magnetic fields of roughly 10 microgas and shock velocities of a few percent of light speed, maximum electron energies reach approximately 10 to the 13th electron volts. Protons, which radiate much less efficiently due to their larger mass, can potentially reach energies 3 orders of magnitude higher, extending into the ultra-high energy cosmic ray regime. Detection of these highest energy particles remains challenging. Electrons radiating at maximum energy produce synchrotron emission, peaking at X-ray frequencies, requiring sensitive space-based telescopes to detect. The Chandra X-ray Observatory has observed several radio galaxy hotspots and detected X-ray emission consistent with synchrotron radiation from multi-trillion electron-volt electrons, confirming that acceleration to extreme energies does occur. Alcyonius has not yet been observed with sufficient X-ray sensitivity to detect or constrain such emission. High-energy protons remain essentially invisible unless they interact with ambient matter to produce gamma rays through p-in decay, or until they escape the source region and reach Earth as cosmic rays. Fermi Gamma Ray Space Telescope observations of nearby radio galaxies have detected gamma ray emission potentially associated with these processes, though interpretation remains debated. The magnetic field topology in the lobes governs how particles move after leaving the acceleration regions. Ordered fields with large coherence lengths allow particles to stream freely along field lines, rapidly filling the lobes with relativistic particles. Tangled fields with small coherence lengths trap particles through pitch-angle scattering, causing them to diffuse slowly through the lobe volume. Observations suggest a mixture of both behaviours, with relatively ordered fields dominating near the jets and increasing disorder toward the lobe edges. This structure naturally arises from the interplay between field lines carried by the jets and turbulence generated by the lobe expansion. The resulting particle distribution is not uniform throughout the lobes, but shows gradients in both density and energy, with the youngest, most energetic particles concentrated near the jets and hotspots. Cosmic ray confinement within the lobes depends critically on the magnetic field's strength and structure. Particles with gyroradii, the radius of their circular motion in the magnetic field, smaller than the lobe dimensions, remain confined and contribute to the radio emission we observe. Particles with gyroradii exceeding the lobe size escape into intergalactic space, joining the population of cosmic rays pervading the universe. For magnetic fields of a few microgauss and lobe dimensions of millions of light years, the maximum energy of confined electrons is roughly 10 to the 13th electron volts, while protons can remain confined to energies approaching 10 to the 18th electron volts. These highest energy, confined protons may contribute to ultra-high energy cosmic ray observations, though proving the connection requires detailed modelling of particle propagation through intergalactic magnetic fields. The topology of intergalactic magnetic fields remains poorly constrained observationally. Multiple mechanisms can generate seed fields in intergalactic space, including primordial fields from the early universe, fields carried by winds and jets from galaxies, and fields generated by plasma instabilities in the ionized intergalactic medium. These fields may be amplified by turbulent motions associated with structure formation, reaching strengths of roughly 1 nanogauss in typical environments. Radio galaxy lobes locally enhance fields by factors of thousands, but beyond the lobes, the ambient intergalactic field determines how escaping cosmic rays propagate. If the field is predominantly uniform on large scales, particles can stream freely and arrive at Earth from their source directions. If the field is tangled on small scales, particles scatter repeatedly and arrive from essentially random directions, obscuring their origins. Rotation measure studies provide the primary observational probe of intergalactic magnetic fields. By measuring how the polarization angle of radio emission from distant sources rotates as it propagates through magnetized plasma, astronomers can infer the line of sight integral of electron density times parallel magnetic field. Statistical analyses of rotation measures toward many sources reveal typical intergalactic field strengths of roughly 1 nanogauss with coherence lengths of roughly 1 million light-years. These measurements remain uncertain due to contributions from multiple magnetized screens along the line of sight, including the Milky Way's own magnetic field, which typically dominates the rotation measure. Disentangling the intergalactic component requires careful modelling and large samples to average over different sight lines. The contribution of Alcyonius to the magnetization of its local cosmic environment proves substantial. The jets have injected magnetic flux equivalent to roughly 10 to the 43 Maxwell into intergalactic space, enough to thread a volume exceeding 20 million light-years in diameter with fields of 1 microgauss. As this magnetized plasma expands and mixes with the surrounding intergalactic medium, it dilutes, but never completely disappears. Magnetic field lines cannot simply vanish. They can only reconnect or stretch to larger scales. The field deposited by Alcyonius will persist for billions of years, slowly decaying through turbulent diffusion and reconnection, but leaving a permanent imprint on the local magnetic field structure. Future generations of galaxies forming in this region will inherit this magnetization, affecting their own evolution and star formation histories. The chemical composition of the lobe plasma reflects the integrated enrichment history of the host galaxy's stellar population. Massive stars synthesize elements heavier than helium through nuclear fusion, with the most massive stars producing elements up to iron through successive burning stages. When these stars explode as supernovae, they eject their enriched material into the interstellar medium, where it mixes with primordial gas and participates in subsequent generations of star formation. Some fraction inevitably finds its way to the galactic center, joining the reservoir of material that feeds the central black hole. The accretion process is not selective. Whatever elements exist in the accreting gas get carried inward and eventually incorporated into the jets. Spectroscopic observations of radio galaxy lobes rarely achieve sufficient sensitivity to detect emission lines from heavy elements directly, but indirect evidence supports the presence of enriched material. X-ray observations of the hot gas in galaxy clusters sometimes reveal emission lines from oxygen, iron, and other metals in regions affected by radio galaxy jets, indicating that the jets transport enriched material from the galaxy into the surrounding medium. For Alcyonius, Noah's Array observations of sufficient depth exist to test this directly, but comparison with similar systems suggests that its lobes likely contain metals at abundances of roughly 10 to 30% of solar values. Over hundreds of millions of years of jet activity, this amounts to millions of solar masses of heavy elements deposited into intergalactic space. The mixing of this enriched material with the pristine intergalactic medium occurs through multiple physical processes. Turbulence generated at the interface between the lobe plasma and external gas creates eddies that fold the two fluids together, gradually homogenizing the composition. Kelvin-Helmholtz instabilities develop along the lobe boundaries, creating characteristic roll-up structures that accelerate mixing. Heat conduction transports thermal energy from the hot lobe plasma to the cooler external gas, while simultaneously allowing diffusion of particle species in the opposite direction. Over timescales of hundreds of millions to billions of years, these processes thoroughly blend the jet material with surrounding gas, distributing the heavy elements across volumes far larger than the visible radio lobes. This chemical enrichment has consequences for subsequent star formation in the region. Heavy elements increase the cooling efficiency of gas, allowing it to radiate energy more effectively and collapse to higher densities. They also provide the raw materials for dust grain formation, which further enhances cooling and eventually contributes to planet formation around stars that form from the enriched gas. The metallicity of the intergalactic medium has risen steadily over cosmic time, as successive generations of stars and active galactic nuclei enrich their surroundings. Alcyonius participates in this cosmic enrichment, adding its contribution to the growing abundance of heavy elements in its corner of the universe. The thermal properties of the lobe plasma differ significantly from the surrounding intergalactic medium. The lobes contain gas heated to temperatures potentially exceeding 100 million degrees by the shocks at the jet termination points and by the dissipation of turbulent energy throughout the lobe volume. This extreme temperature gives the plasma high thermal pressure, allowing the lobes to expand against the external medium. However, the particle density in the lobes remains low, similar to or even lower than the external density, so the total thermal energy content is not as enormous as the temperature alone might suggest. The pressure balance between the thermal pressure, the magnetic pressure, and the external pressure determines the lobe dynamics and morphology. Detailed pressure balance calculations for radio galaxy lobes typically find that magnetic pressure dominates over thermal pressure, meaning the lobes are magnetically supported rather than thermally supported. This conclusion follows from combining radio observations that constrain magnetic field strength with X-ray observations that constrain thermal pressure. For Alcyonius, no direct X-ray measurements exist, but comparison with similar sources suggests that the magnetic pressure likely exceeds thermal pressure by a factor of several. This magnetically dominated state arises naturally in relativistic jets where the magnetic field is dynamically important in confining and accelerating the flow. The ratio of thermal to magnetic pressure, often called the plasma beta, appears to be less than unity in most radio galaxy lobes. The work done by the lobes against the external pressure as they expand represents a significant energy sink. Each time the lobe doubles in size, it must displace 8 times as much volume of external gas, doing work against the pressure of that gas. The energy required increases with the cube of the lobe size, meaning that growth from 10 million to 16 million light-years requires substantially more energy than growth from 0 to 10 million light-years. This effect may naturally limit how large lobes can grow, as the power required to continue expansion eventually exceeds what the jets can supply. However, for Alcyonius, the jets appear to remain sufficiently powerful to drive ongoing expansion, suggesting that this limit has not yet been reached. Hydrodynamic simulations of lobe expansion reveal complex flow patterns within the lobes. Hot shocked material at the hotspots flows backward along the jet axis, filling the lobe volume through a combination of advection and turbulent mixing. Cooler material from the external medium gets entrained at the lobe boundaries, mixing inward and contributing to the lobe mass. The resulting flow pattern resembles a large-scale circulation cell, with fresh material entering through the hotspots, aging as it circulates through the lobe, and eventually mixing with external gas at the lobe boundaries. The timescale for a particle to circulate through the entire lobe volume ranges from tens to hundreds of millions of years, depending on lobe size and flow velocities. The timescale for complete lobe replacement, the time required for the jets to inject enough new material to completely replace the existing lobe contents, provides another important characteristic time. This replacement time equals the total mass and energy content of the lobes divided by the mass and energy injection rate through the jets. For Alcyonius, estimates suggest replacement times of several 100 million years, comparable to the estimated age of the lobes. This near equality indicates that the lobes contain primarily material injected relatively recently in cosmic terms, with little contribution from very early phases of jet activity. Older material has either mixed into the external medium or radiated away its energy to the point of undetectability. The influence of Alcyonius on nearby galaxies extends beyond direct heating and chemical enrichment. The pressure waves generated by the expanding lobes propagate through the intergalactic medium, potentially triggering or suppressing star formation in galaxies they encounter. Compression of gas by passing shocks can push it above the density threshold for gravitational collapse, initiating star formation that might not have occurred otherwise. Conversely, heating by the shocks can raise gas temperatures enough to prevent collapse, quenching star formation. The balance between these competing effects depends on details of the gas properties and the shock strength. Simulations of radio galaxy feedback show both positive and negative effects on star formation in different circumstances. Galaxy surveys searching for correlations between radio galaxy locations and star formation rates in neighbouring galaxies have produced ambiguous results. Some studies find modest evidence that star formation is suppressed near powerful radio galaxies, consistent with heating effects dominating. Other studies find no significant correlation or even weak evidence for enhanced star formation, suggesting that triggering effects can balance suppression. The difficulty in drawing firm conclusions stems from the small numbers of well-studied examples and the challenge of isolating radio galaxy effects from other environmental factors that also affect star formation. Alcyonius, with its extreme size, might show clearer effects if a sensitive survey of star formation in its neighbourhood could be conducted. The gravitational influence of Alcyonius on its cosmic environment remains negligible, despite the enormous spatial extent of its radio lobes. The total mass in the lobes amounts to perhaps 100 million solar masses, small compared to the mass of the host galaxy at roughly 240 billion solar masses, and tiny compared to the dark matter, halo mass, likely exceeding 1 trillion solar masses. The lobe's gravitational effect extends only as far as their mass distribution, making no significant contribution to the large-scale gravitational field. Their impact comes entirely through non-gravitational processes: heating, chemical enrichment, momentum deposition, and magnetization. These processes affect the thermodynamic state of the intergalactic medium and the conditions for galaxy formation, but leave the large-scale gravitational structure unchanged. The eventual fate of Alcyonius depends on the future evolution of its central black hole and the availability of fuel for continued accretion. If the current accretion rate of roughly 1 solar mass per year continues indefinitely, the black hole will double its mass in roughly 400 million years, However, fuel supplies are finite. The galaxy contains perhaps 10 to 100 billion solar masses of hot gas in its halo, but most of this gas sits in hydrostatic equilibrium and will not accrete without some mechanism to remove its angular momentum and allow infall. Cooling flows can supply accretion at rates of a few solar masses per year, sufficient to maintain current activity levels, but this process is self-limiting as jet feedback heats gas and suppresses cooling. The balance suggests that accretion can continue at current rates for several 100 million more years before fuel depletion or feedback effects cause activity to decline. When accretion eventually drops below the threshold for sustained jet production, the lobes will enter their relic phase. The jets will sputter and cease, cutting off the supply of fresh particles and energy. The lobes will continue expanding briefly due to their internal pressure, but will soon begin contracting as particle losses exceed what the residual pressure can support. The radio emission will fade as electrons radiate away their energy and no new particles arrive to replace them. The timescale for fading depends on the particle energy distribution and magnetic field strength. Estimates suggest that lobes like those of Alcyonius remain detectable for several 100 million years after jet shutdown, potentially longer at the lowest radio frequencies where sensitivity to aged populations proves greatest. During this relic phase, the lobes transform from actively energy-fed structures to passively evolving bubbles of hot magnetized plasma. The magnetic field weakens as the plasma expands, and turbulent dissipation converts magnetic energy to heat. The particle population ages beyond detectability, with the highest energy particles disappearing first as they radiate most rapidly. The thermal energy content decreases as the plasma does work against the external pressure and as conduction transports heat to the surrounding medium. Eventually, after perhaps 1 billion years, the former lobe regions become indistinguishable from their surroundings, except for lingering enhancements in metallicity, temperature, and magnetic field strength. Even these signatures gradually fade as mixing and diffusion homogenize the region. The possibility of episodic activity introduces additional complexity. Rather than maintaining constant jet power for hundreds of millions of years followed by permanent shutdown, the black hole might cycle through multiple episodes of activity separated by quiescent periods. Each active episode would reinflate the lobes or create new lobe structures beyond the old ones, building a complex multi-generation morphology. Evidence for such episodic behavior appears in some radio galaxies displaying multiple pairs of lobes or wings extending in different directions. Alcyonius shows no clear signs of previous episodes, suggesting either that this is its first major active phase or that earlier episodes left no detectable remnants. The absence of visible older lobes places limits on how recently previous episodes could have occurred. The relationship between Alcyonius and the overall population of active galactic nuclei reveals insights into the duty cycles and lifetimes of black hole accretion episodes. Statistical studies estimate that roughly 1% of massive elliptical galaxies host active radio sources at any given time. This fraction, combined with estimates of typical radio source lifetimes of tens of millions of years, implies that most massive galaxies experience radioactivity during a few percent of their lifetimes. Alcyonius, with its hundreds of millions of years of activity, represents an unusually long-lived example. Either such extended episodes occur rarely, perhaps once per 100 typical episodes, or the duty cycle statistics require revision based on improved understanding of source lifetimes and detection biases. The correlation between radio galaxy activity and galaxy merger history has been studied extensively, with mixed conclusions. Early work suggested that powerful radio galaxies preferentially occur in galaxies showing signs of recent mergers, supporting models where mergers funnel gas toward galactic centers and trigger black hole accretion. More recent studies with larger samples find weaker correlations, particularly for lower power radio sources and sources in the local universe. Alcyonius's apparently undisturbed morphology and old stellar population suggest it has not experienced major mergers in billions of years, yet it hosts one of the most extreme radio sources known. This indicates that mergers, while potentially important triggers, are not the only pathway to sustained radioactivity. Secular processes that operate without mergers can also supply fuel to central black holes. Gravitational torques from non-axis symmetric structures like bars or spiral arms can drive gas inward from large radii. Stellar mass loss from the old stellar population continuously adds gas to the galactic halo, some fraction of which eventually reaches the center. minor mergers with satellite galaxies deliver gas without causing major morphological disturbances. The combination of these processes can maintain modest accretion rates over extended periods, potentially explaining sources like Alcyonius that display sustained activity without obvious recent major mergers. The key requirement is not necessarily large instantaneous accretion rates, but rather consistency over timescales of hundreds of millions of years. The spin evolution of the central black hole provides another window into its accretion history. Black holes can spin up through prolonged accretion or spin down through chaotic accretion from different directions that delivers opposing angular momentum. A black hole that has accreted steadily from a stable accretion disk over its lifetime should have high spin, potentially near the maximum allowed by general relativity. A black hole with a more chaotic accretion history, experiencing multiple episodes from different orientations, should have lower spin. Alcyonius's apparently stable jet geometry suggests that its black hole has maintained a consistent spin axis orientation for at least the duration of the current radio episode, though whether it possesses high or low total spin remains unknown without direct measurements. Measuring black hole spin requires observations that probe the innermost regions of the accretion flow where relativistic effects become important. X-ray spectroscopy of the ion emission line from the inner accretion disk can reveal the characteristic relativistic distortions caused by black hole spin. X-ray timing studies of variability can detect quasi-periodic oscillations whose frequencies depend on the orbital properties near the innermost stable circular orbit, which varies with spin. Neither technique has been successfully applied to Alcyonius due to its moderate luminosity and large distance. Future X-ray observatories with improved sensitivity may enable such measurements, finally revealing whether extreme radio galaxy size correlates with extreme black hole spin. The efficiency of jet production, defined as the ratio of jet power to accretion power, varies widely among active galactic nuclei. Some systems convert more than 10% of their accretion energy into jet kinetic energy, approaching theoretical maximum efficiencies. Others produce weak or no jets despite accreting at substantial rates, suggesting inefficient conversion. The factors controlling this efficiency remain debated. Black hole spin likely plays a role, with rapidly spinning holes potentially producing more powerful jets through the Blandford-Znajek mechanism. The magnetic flux threading the black hole also matters, as this flux provides the field lines along which jets are launched. The accretion rate relative to Eddington may influence efficiency, with low accretion rates favouring jet-dominated systems. Alcyonius's jet power of roughly 10 to the 42 ergs per second, compared to an estimated accretion power of perhaps 10 to the 44 ergs per second, implies an efficiency of roughly 1%. This places it in the typical range for radio-loud active galactic nuclei, neither exceptionally efficient nor inefficient. The efficiency consistent with typical values suggests that Alcyonius' extreme size arises not from unusually powerful jets, but from favourable environmental conditions and exceptional longevity. A jet of ordinary power, given sufficient time and a clear path through intergalactic space, can build structures larger than jets, orders of magnitude more powerful that encounter adverse conditions or remain active for shorter periods. The concept of a radio-loud versus radio-quiet dichotomy in active galactic nuclei has evolved, as observations have revealed a continuum of radio properties rather than a strict bimodality. Early classifications divided active galactic nuclei into radio-loud sources with strong jets and radio-quiet sources with weak or absent jets. The radio-loud sources appeared preferentially in elliptical galaxies, while radio-quiet sources occurred more often in spiral galaxies, suggesting that host galaxy morphology influences jet production. Modern surveys with improved sensitivity detect radio emission from virtually all active galactic nuclei, revealing that the distinction lies in the strength rather than the presence or absence of radioactivity. Alcyonius represents the extreme radio-loud end of this continuum. The question of what determines whether a galaxy falls on the radio-loud or radio-quiet end of the spectrum involves multiple factors that remain incompletely understood. The most widely accepted framework involves black hole spin magnitude and orientation, with rapidly spinning black holes aligned with their accretion disks producing powerful jets. The magnetic field configuration in the accretion flow also proves crucial, as strong large-scale fields threading through the inner accretion region can tap the black hole's rotational energy efficiently. The accretion rate matters as well, with lower rates favouring the radiatively inefficient accretion flows that produce stronger jets. No single parameter fully explains the observed distribution, suggesting that jet production requires a conjunction of favourable conditions rather than depending on one dominant factor. Environmental factors external to the galaxy may also influence radio loudness. Galaxies in dense environments experience ram pressure as they move through hot intracluster gas, which can strip gas from their disks and halos. This stripping might preferentially remove the rotating gas that would form a thin accretion disk, leaving behind primarily hot gas that accretes through radiatively inefficient flows conducive to jet production. Conversely, galaxies in underdense environments retain their gas reservoirs more easily, but may lack the supply of fresh material that major mergers would provide. Alcyoneus, in its relatively sparse environment, demonstrates that underdense regions can still supply sufficient fuel for sustained powerful jets, though whether this occurs through different mechanisms than in denser environments remains unclear. The absence of strong optical emission lines in Alcyoneus' spectrum indicates that it belongs to the class of low-excitation radio galaxies rather than high-excitation radio galaxies. High-excitation radio galaxies display strong emission from highly ionized species, indicating the presence of intense ultraviolet radiation from an efficient accretion disk. Low-excitation radio galaxies lack these strong lines, consistent with radiatively inefficient accretion where less radiation escapes to ionize surrounding gas. The correlation between excitation class and radio power is not absolute, but low-excitation radio galaxies tend to have lower accretion rates relative to Eddington. Alcyoneus fits this pattern, combining powerful radio emission with relatively modest optical and ultraviolet luminosity characteristic of inefficient accretion. The evolution of radio galaxy populations over cosmic time provides context for understanding objects like Alcyoneus. At high redshifts, corresponding to the first few billion years after the Big Bang, radio galaxies show systematically higher luminosities and more compact sizes compared to present-day examples. This evolution reflects both the changing availability of fuel for black hole growth and the increasing size of the universe itself. Young galaxies in a denser universe experience more frequent mergers and possess larger gas reservoirs, enabling intense but brief episodes of radioactivity. As the universe expands and galaxies deplete their gas through star formation, radioactivity transitions to the lower luminosity, longer-lived mode exemplified by Alcyoneus. Cosmic downsizing describes the phenomenon where the most massive galaxies completed their main growth and star formation activity earlier in cosmic history than less massive galaxies. This downsizing extends to black hole growth and radioactivity, with the most powerful radio sources peaking in abundance at redshifts around 2 to 3, corresponding to look-back times of 10 to 11 billion years. Lower power sources like Alcyoneus dominate at more recent epochs. This pattern suggests an evolutionary sequence where violent activity in youth gradually gives way to quiescent old age, punctuated by occasional episodes of moderate activity. Alcyoneus represents this late time phase, a mature system experiencing one more episode of modest sustained activity, billions of years after its vigorous youth ended. The prospect of observing Alcyoneus at multiple cosmic epochs through gravitational lensing offers an intriguing possibility, though one that remains purely theoretical given current observational capabilities. Gravitational lensing by massive foreground structures can create multiple images of background sources, with the images showing the source at different times due to the different path lengths light travels along different lensing paths. Time delays between images can range from days to years depending on the lens configuration. For a source at Alcyoneus redshift lensed by a massive cluster, time delays might reach several years. Monitoring such a lensed system over decades could potentially reveal variability in the jets or hotspots, providing direct measurements of jet evolution timescales. However, no known strongly lensed system displays a giant radio galaxy of comparable size. The future observational prospects for studying Alcyoneus and similar objects continue to improve as new facilities come online. The Square Kilometre Array, currently under construction in South Africa and Australia, will provide sensitivity orders of magnitude better than existing radio telescopes across frequencies from 50 MHz to several GHz. This unprecedented sensitivity will enable detection of giant radio galaxies to much greater distances and will reveal their properties with far greater detail. Structures currently visible only as diffuse patches will resolve into intricate networks of filaments and substructures. Spectral mapping will trace particle aging patterns with precision, constraining models of particle transport and energy loss. Polarization studies will reveal magnetic field structures throughout the lobes at multiple frequencies. The next generation, Very Large Array planned for construction in the continental United States will complement the Square Kilometre Array with even higher angular resolution at frequencies from 1 to 100 GHz. This resolution will resolve the jets and inner lobe structures of systems like Alcyonius down to scales of thousands of light years, revealing details of how jets maintain collimation and how they interact with the ambient medium. Time domain observations tracking variations over months to years will constrain jet speeds and hotspot advance rates directly rather than through modelling. Combining observations from multiple facilities spanning frequencies from tens of megahertz to tens of gigahertz will provide complete spectral coverage, enabling robust physical modelling. The discovery of Alcyonius raises fundamental questions about whether we have found the largest possible radio galaxy or merely the largest one detectable with current technology. Physical arguments suggest that true upper limits on lobe size must exist, imposed by the finite lifetime of jet activity, the increasing resistance of the intergalactic medium at large distances, and the eventual exhaustion of fuel supplies. However, the specific size at which these limits become insurmountable remains uncertain. Theoretical models propose maximum sizes ranging from 20 to 50 million light-years, depending on assumptions about environmental density, jet power, and activity duration. Alcyonius, at 16.3 million light-years, sits comfortably below even the most conservative estimates, suggesting that larger structures remain physically plausible. Observational selection effects severely bias our sensors of giant radio galaxies towards smaller and brighter examples. Detection requires that the surface brightness, the amount of radio emission per unit area on the sky, exceeds the noise level of the survey. As lobes expand, their emission spreads across larger areas, while the total luminosity may not increase proportionally, causing surface brightness to decrease. Sources with sufficiently low surface brightness remain invisible regardless of their total luminosity. This effect becomes particularly severe for giant radio galaxies, whose lobes extend across degrees on the sky. Survey designs optimized for detecting compact bright sources systematically miss extended diffuse structures, even when those structures contain more total energy. LOFA's success in finding Alcyonius stems from its combination of low-frequency operation and imaging techniques specifically designed to preserve sensitivity to extended emission. Traditional interferometric imaging employs Fourier transforms that naturally emphasize compact structures, while filtering out extended emission on angular scales larger than the shortest baseline in the array. This filtering proves essential for achieving high angular resolution, but comes at the cost of missing large-scale structure. LOFA combats this effect by including short baselines in its array configuration and by employing imaging algorithms that account for the filtering and attempt to recover extended emission. Even with these advances, truly giant structures approaching 20 or 30 million light-years at Alcyonius's distance might still escape detection if their surface brightness falls too low. The angular size on the sky provides another detection challenge. Alcyonius subtends roughly 6 arc minutes from end to end, comparable to the field of view of many radio telescopes. Larger sources at similar distances would exceed typical survey pointings, requiring mosaic observations that tile multiple fields together to capture the full extent. Such mosaics demand significantly more observing time and introduce additional calibration challenges where fields overlap. Many surveys avoid these complications by focusing on smaller fields, observed deeply rather than large areas observed shallowly. A radio galaxy 25 million light-years across at Alcyonius's distance would span nearly 10 arc minutes, likely straddling multiple survey pointings and potentially being missed entirely if each pointing analysed independently failed to recognise the emission as parts of a single coherent structure. Sky coverage limitations in existing surveys mean that vast regions remain unexplored at the depth and resolution needed to find giants like Alcyonius. LOFA's deepest surveys have covered only a few thousand square degrees, roughly 10% of the total sky. The remaining 90% may contain dozens or hundreds of similar objects awaiting discovery. Statistical arguments based on the density of giant radio galaxies in surveyed regions suggest that the entire sky should contain several thousand systems with lobes exceeding 10 million light-years. Among these, the largest handful should extend beyond 20 million light-years if the size distribution follows the power law extrapolation from smaller sources. The challenge lies in developing survey strategies and data processing pipelines capable of identifying such rare, extended objects efficiently. Distance effects compound these challenges. Cosmological dimming reduces the observed brightness of distant sources by factors that increase rapidly with redshift. A source at redshift 1 appears 16 times fainter than an identical source at redshift 0.25, making detection far more difficult. Giant radio galaxies at high redshift must possess exceptional intrinsic luminosity to remain detectable, biasing surveys toward the most powerful examples and missing the moderate luminosity long-lived sources that may dominate the population. Alcyonius's moderate redshift places it in an optimal range for detection, close enough that cosmological dimming remains manageable, but far enough that many similar objects should exist within the survey volume. Pushing detection to higher redshifts requires enormous investments in observing time or awaits next-generation facilities. The population of giant radio galaxies as a function of size appears to follow a steeply declining distribution, with numbers dropping by factors of several for each doubling in size. This statistical pattern, if it continues to the largest sizes, predicts that 20 million light-year giants should be roughly 5 times rarer than 16 million light-year giants, and 30 million light-year giants another 5 times rarer still. Given the limited sky coverage and sensitivity of current surveys, finding examples at these extreme sizes requires either surveying much larger areas or significantly increasing survey depth. The square kilometre array should achieve both goals, potentially revealing whether the size distribution continues its power law decline or whether it steepens or truncates at large sizes, indicating a physical limit. Environmental surveys measuring the density distribution of the intergalactic medium around known giant radio galaxies provide empirical constraints on how large lobes can grow. These surveys use the absorption of distant quasar light by intervening hydrogen to map gas density along multiple lines of sight near the target galaxy. Results show that giant radio galaxies preferentially inhabit regions where intergalactic medium density remains below the cosmic average by factors of 2 to 5. Extending this correlation suggests that 30 million light-year giants, if they exist, should occupy the most underdense regions of the cosmic web, the centres of voids where galaxy densities drop to 10% or less of average. Such extreme environments are rare, occupying perhaps 5% of cosmic volume, immediately constraining where to search for the largest systems. Void environments present their own observational challenges. The lack of nearby galaxies means fewer optical identifications to guide searches and greater difficulty confirming redshifts for host galaxies. Radio emission from giant radio galaxies in voids must be detected and characterized based primarily on morphology and radio properties alone, without the supporting context that dense environments provide. Additionally, voids tend to be located away from the well-studied regions of sky where galaxy surveys have concentrated, requiring dedicated observations of less characterized areas. These factors have likely caused existing surveys to undersample the void population, potentially missing the largest radio galaxies. The finite speed of light introduces another consideration when discussing observable limits. We observe Alcyonius as it existed 3 billion years ago, when the light we detect began its journey. The galaxy continues evolving during the light travel time, potentially growing larger or entering a quiescent phase. Our census of giant radio galaxies represents a snapshot of the population at various epochs, depending on each source's distance. The largest observable structure at any given moment includes contributions from different cosmic times, with nearby sources showing their current state, while distant sources display their ancient history. This temporal mixing complicates interpretation of size distributions and evolution patterns. Projection effects create additional uncertainty in determining true three-dimensional sizes. We observe radio lobes projected onto the plane of the sky, unable to directly measure their extent along our line of sight. Statistical arguments suggest that viewing angles distribute randomly, allowing conversion from observed angular sizes to physical sizes using average projection factors. However, individual sources can deviate substantially from averages. Alcyonius might be oriented nearly perpendicular to our line of sight, showing its full extent, or it might have significant components along our line of sight that make its true size larger than measured. Conversely, two unrelated radio sources might align by chance along our line of sight, creating the appearance of a single giant system. Resolving these ambiguities requires independent distance measurements at multiple positions or detailed modelling of lobe dynamics. The question of whether galaxy morphology limits maximum radio galaxy size merits examination. Elliptical galaxies like Alcyonius's host dominate the giant radio galaxy population, but whether this reflects physical requirements or selection effects remains debated. Elliptical galaxies possess hot gaseous halos extending well beyond their stellar distributions, providing reservoirs of material that can fuel sustained accretion. Spiral galaxies contain more cold gas, but typically in rotationally supported disks rather than quasi-spherical distributions. The different gas geometries might affect accretion onto central black holes and jet launching, favouring ellipticals for producing sustained powerful jets. Alternatively, spiral galaxies might produce giant radio galaxies as frequently as ellipticals, but remain underrepresented in surveys due to higher extinction from dust or orientation effects. Mergers between galaxies hosting active radio sources introduce the possibility of binary radio galaxies with multiple pairs of lobes emanating from different positions. If two galaxies each containing active supermassive black holes merge, the resulting system temporarily contains two black holes that sink toward the centre through dynamical friction. During this sinking phase, both black holes might remain active, producing two sets of jets and lobes. The combined structure could extend across distances exceeding what either galaxy could achieve alone. However, such systems should be rare and short-lived compared to the timescales for lobe growth, making them unlikely to dominate the population of the larger structures. Searchers for dual radio galaxies have identified a few candidates, but none approaching Alcyonius's size. Environmental preprocessing of the intergalactic medium by earlier generations of radio galaxies might enable or inhibit growth of subsequent giants. A region that has been heated and magnetized by previous radioactivity contains gas at lower density and higher entropy, potentially allowing jets to propagate more easily. Alternatively, the magnetic fields left by previous sources might deflect or confine jets from later sources, affecting their trajectories and ultimate sizes. The typical separation between radio galaxies in space averages several tens of millions of light years, comparable to the size of the largest giants. This suggests that large radio galaxies frequently operate in environments modified by earlier activity, though quantifying these effects requires detailed simulations of the cumulative impact of multiple sources. The duty cycle of radioactivity determines how often giant radio galaxies operate at full power versus lower power states or quiescence. If radio galaxies cycle between active and inactive phases on timescales shorter than lobe growth times, reaching extreme sizes requires that the active phases substantially outweigh the inactive phases. Conversely, if radio sources remain continuously active once triggered, the duty cycle proves less relevant. Observational evidence supports episodic activity in at least some radio galaxies, as revealed by multiple generations of lobes at different evolutionary stages. Whether Alcyonius operates continuously or episodically affects interpretation of its age and predictions about its future evolution. The concept of frustrated radio sources, jets that fail to break out of their host galaxy's interstellar medium and remain confined to galactic scales, provides a counterpoint to giants like Alcyonius. These compact steep spectrum sources and gigahertz peaked spectrum sources display radio morphologies spanning only thousands of light years despite being powered by jets with energies comparable to those of large radio galaxies. Two competing explanations for their compact nature have been proposed. The youth scenario suggests they represent young radio sources that will eventually grow to large sizes if given sufficient time. The frustration scenario proposes that dense gas in their host galaxies permanently confines the jets, preventing escape to intergalactic space. If frustration proves common, it places a selection effect on which galaxies can produce giant radio sources, requiring not just powerful jets, but also relatively low-density interstellar media that permit jet escape. Observational tests attempting to distinguish between youth and frustration scenarios have produced mixed results. Some compact sources show spectral and morphological properties consistent with youth, suggesting ages of only thousands to tens of thousands of years. Others display signatures of aged particle populations despite their compact sizes, supporting the frustration interpretation. The existence of both populations implies that some compact sources will evolve into giants, while others remain permanently confined. The fraction of radio sources that successfully break out and begin growing large lobes determines how common objects like Alcyonius can ultimately become. If only 10% of nascent radio sources escape their host galaxies, the population of giants reflects this bottleneck regardless of environmental conditions at larger scales. The relationship between radiomorphology and black hole spin axis evolution adds another dimension to understanding size limits. Lens-Thirring precession causes misaligned accretion disks to torque the black hole spin axis, gradually bringing the two into alignment. This process occurs over timescales ranging from thousands to millions of years, depending on the black hole mass and accretion rate. During the alignment phase, the jet direction changes as it follows the evolving spin axis, potentially creating bent or twisted radiomorphologies. Alcyonius's straight jets indicate that any initial misalignment has been resolved, allowing stable jet directions for the duration of lobe growth. Sources experiencing significant precession might never achieve extreme sizes, because the continuously changing jet direction prevents coherent lobe growth in fixed directions. X-shaped radio galaxies represent a distinct morphology, where two pairs of lobes extend in different directions from the same host galaxy. The primary lobes align with the current jet axis, while secondary wings extend at large angles, sometimes approaching perpendicular to the primary axis. Multiple explanations for this morphology have been proposed, including jet reorientation following galaxy mergers, backflow of lobe material along paths of least resistance, or hydrodynamic effects in the intergalactic medium. If jet reorientation proves common, it limits how long jets maintain fixed orientations and therefore constrains maximum achievable lobe sizes along any single axis. However, X-shaped morphologies remain rare, appearing in only a few % of radio galaxies, suggesting that most sources maintain stable jet orientations throughout their active lifetimes. The total energy budget of radio galaxies over cosmic history represents a significant contributor to the energy content of the intergalactic medium. Estimates suggest that active galactic nuclei, including radio galaxies, have injected roughly 10 to the 61 ergs per cubic megaparsec into intergalactic space since Redshift 2. This energy density exceeds by factors of several the energy deposited by supernova explosions from star formation, establishing active galactic nuclei as the dominant heating mechanism in regions outside dense galaxy clusters. Giant radio galaxies like Alcyonius contribute disproportionately to this heating despite their rarity, because each source affects such large volumes. A single giant distributes its energy across volumes of hundreds of cubic megaparsecs, heating gas that might otherwise cool and form stars in future generations of galaxies. This heating affects the baryon budget of the universe in observable ways. Cosmological measurements of the total baryon density from Big Bang nuclear synthesis and cosmic microwave background observations establish that baryons constitute roughly 16% of the total matter density. However, direct census of observed baryons in stars, cold gas, and hot X-ray emitting gas accounts for only about half this total. The missing baryons likely reside in warm, hot intergalactic medium with temperatures between 100,000 and 10 million degrees, too cool to emit detectable X-rays, but too hot to produce strong absorption lines in ultraviolet spectra. Radio galaxy heating maintains gas in precisely this temperature range, potentially explaining a significant fraction of the missing baryons. Giant radio galaxies heat particularly large volumes to these intermediate temperatures, making them key players in solving the missing baryon problem. The metallicity distribution in the intergalactic medium provides another cosmological diagnostic, where radio galaxies prove important. Chemical evolution models predict that the mean metallicity of intergalactic space should reach roughly 10% of solar values by the present epoch, reflecting billions of years of enrichment by stellar winds and supernova ejecta. Observations of absorption lines in quasar spectra generally confirm this prediction for overdense regions along filaments, but measurements in underdense regions show more scatter and lower mean metallicities. Radio galaxies may help explain this pattern by transporting metals from galaxies into voids, establishing metallicity flaws even in regions that would otherwise remain pristine. Alcyonius, extending across a substantial void fraction, contributes directly to this metal transport. The magnetic field structure of the cosmic web represents another area where giant radio galaxies provide crucial information. Primordial magnetic fields from the early universe, if they exist, should have strengths below 1 nanogauss by the present epoch after being diluted by cosmic expansion. Measurements of rotation measures toward distant radio sources suggest field strengths of roughly 1 nanogauss with coherence lengths of order 1 megaparsec, implying that the fields we observe are not primordial but were generated and amplified by astrophysical processes. Radio galaxies contribute to this amplification both directly by injecting magnetized plasma and indirectly by driving turbulence that amplifies seed fields. The cumulative effect of billions of radio sources over cosmic time may have magnetized the cosmic web to observed levels, with giants like Alcyonius magnetizing volumes far larger than typical sources. Galaxy formation efficiency, the fraction of available baryons that form stars, varies systematically with galaxy mass in ways that feedback from active galactic nuclei helps explain. Low-mass galaxies convert only a few % of their baryons into stars, with the remainder expelled by supernova-driven winds. The most massive galaxies also show low efficiencies despite having deep enough potential wells to retain supernova ejecta, suggesting that some other feedback mechanism suppresses star formation. Radio galaxy jets provide the necessary heating to prevent gas from cooling in massive galaxies, maintaining hot halos that cannot collapse to form stars. The correlation between galaxy mass and radioactivity supports this picture, with the most massive galaxies hosting the most powerful radio sources. Alcyonius, in a galaxy of roughly 240 billion solar masses, exemplifies this regime where radio feedback dominates. The colour bimodality of galaxies, the division between blue star-forming galaxies and red quiescent galaxies, also implicates active galactic nucleus feedback. Galaxies appear to transition relatively rapidly from the blue cloud to the red sequence, rather than populating intermediate colours, suggesting that the quenching of star formation occurs quickly once triggered. Radio galaxies provide a mechanism for this rapid quenching by heating gas throughout the galaxy halo on timescales of tens of millions of years, comparable to the apparent timescale for the colour transition. The fraction of galaxies hosting radio sources increases dramatically in the transition region between blue and red, consistent with radioactivity playing a causal role in driving galaxies from one population to the other. Large-scale structure statistics measured through galaxy surveys and cosmic microwave background observations constrain cosmological parameters including the matter density, dark energy density, and amplitude of primordial density fluctuations. These measurements assume that baryonic physics affects structure formation only on small scales below a few megaparsecs, allowing baryons to be treated as a collisionless fluid like dark matter on larger scales. However, radio galaxy feedback operates on scales approaching 10 megaparsecs for giants like Alcyonius, potentially violating this assumption. If feedback significantly affects the baryon distribution on these scales, it introduces systematic errors in cosmological parameter estimation. Current analyses suggest these effects remain small, but precision cosmology with future surveys may require explicit modelling of radio galaxy feedback. The technological frontier of radio astronomy continues advancing at a pace that promises transformative discoveries over the coming decades. The Square Kilometre Array represents the most ambitious radio telescope project ever undertaken, designed to achieve collecting area approaching 1 square kilometre, distributed across thousands of individual antennas. Construction proceeds in 2 phases, with SKA Low in Australia covering frequencies from 50 to 350 MHz, and SKA Mid in South Africa, spanning 350 MHz to 15.4 GHz. When completed, these facilities will provide sensitivity 50 times greater than existing instruments, enabling detection of radio sources at unprecedented distances and revealing faint structures invisible to current surveys. For giant radio galaxies, this sensitivity translates directly into discovery potential, with estimates suggesting SK will detect tens of thousands of systems comparable to or larger than Alcyonius. The survey speed of SKA, the rate at which it can map large areas of sky to given sensitivity levels, exceeds current facilities by factors of hundreds. This efficiency emerges from the combination of large collecting area and wide field of view enabled by phased array feeds and advanced signal processing. SK will conduct all sky surveys reaching sensitivities that current instruments achieve only in small targeted regions, ensuring complete census of giant radio galaxies across the observable universe. The surveys will operate continuously, building up integration time over years to reach ultimate sensitivity limits, while also enabling time-domain studies that track variability and proper motions. This temporal dimension adds entirely new capabilities for studying jet evolution and lobe dynamics directly rather than inferring them from static snapshots. Spectral resolution represents another area where SKA advances the state of the art. Current observations typically employ bandwidths divided into dozens to hundreds of frequency channels, sufficient for measuring spectral indices but inadequate for detailed spectral tomography. SKA will provide thousands of channels spanning its full bandwidth, enabling reconstruction of three-dimensional spectral cubes, where each position on the sky has a complete radio spectrum. These spectral cubes will reveal subtle features invisible in broadband observations, including spectral breaks indicating particle energy cutoffs, spectral curvature constraining energy loss timescales, and narrow features from thermal emission or recombination lines. For Alcyonius, such observations would map the spectral aging pattern throughout the lobes with unprecedented detail, constraining particle injection histories and magnetic field evolution. Polarimetric capabilities of SKA will revolutionize studies of magnetic fields in radio galaxies and the intergalactic medium. Full-Stokes polarimetry across wide bandwidths will provide rotation measure synthesis, a technique that disentangles multiple magnetized screens along the line of sight and reveals the three-dimensional structure of magnetic fields. This capability will map not just the fields within Alcyonius's lobes, but also the fields in the intergalactic medium between the lobes and Earth, constraining field strengths and coherence lengths throughout the cosmic web. Combining rotation measure data from thousands of giant radio galaxies will construct statistical models of intergalactic magnetism, testing theories of magnetic field generation and evolution over cosmic time. The next generation. Very Large Array planned for the United States will provide complementary capabilities emphasizing higher frequencies and angular resolution. Operating from 1 to 116 GHz with baselines extending 1,000 km, GVLA will resolve structures down to millisecond scales, equivalent to light years at cosmological distances. This resolution will image the jets and inner lobes of systems like Alcyonius with clarity comparable to current observations of nearby radio galaxies, revealing jet collimation mechanisms, shock structures, and particle acceleration sites. Time-domain observations will track jet speeds and hotspot advance rates directly, measuring quantities that currently require indirect inference from models. The combination of SKA surveying vast volumes and NGVLA, providing detailed imaging of selected targets, will create synergistic science impossible with either facility alone. Space-based radio astronomy offers unique advantages for certain observations despite the practical challenges of deploying large antennas beyond Earth's atmosphere. Satellites in Earth, orbit, or positioned at Lagrange points can observe at frequencies below 10 MHz blocked by Earth's ionosphere, accessing the lowest frequency emission from the most aged particle populations in giant radio galaxy lobes. These observations probe particle ages exceeding 1 billion years, potentially detecting relic structures long after they fade from ground-based surveys. Space interferometry, connecting orbital antennas to ground arrays, also enables baselines exceeding Earth's diameter, achieving angular resolutions of microarc seconds that resolve jet launching regions and test models of black hole spin and magnetic field geometry. Multi-messenger astronomy, combining radio observations with data from other wavelength regimes and from non-electromagnetic messengers, promises comprehensive understanding of systems like Alcyonius. X-ray observations with missions like Athena and Lynx will measure the thermal properties of shocked gas in the lobes and detect inverse Compton emission from the highest energy electrons. Gamma-ray telescopes, including the Cherenkov telescope array, will search for emission from ultra-high energy particles and test whether radio galaxies contribute significantly to the cosmic ray spectrum. gravitational wave detectors may eventually achieve sensitivity to detect mergers of the supermassive black holes powering radio galaxies, providing independent measurements of black hole masses and spins. Neutrino detectors scanning the high-energy sky may identify radio galaxies as sources if hadronic acceleration processes operate in their jets. Machine learning techniques applied to radio survey data will accelerate the discovery and characterization of giant radio galaxies. Training neural networks to recognize the morphological signatures of extended radio lobes enables automated classification of millions of sources in survey catalogues, identifying candidates for detailed follow-up. Generative models can interpolate between observed frequencies to predict source appearance across the full radio spectrum, guiding observing strategies and optimizing integration times. Anomaly detection algorithms identify unusual sources that deviate from standard patterns, potentially revealing new classes of objects or exceptional examples like Alcyonius that push beyond known size limits. These computational tools become essential as survey data volumes exceed human capacity for visual inspection and manual classification. Citizen science projects engaging public volunteers in radio galaxy classification have demonstrated remarkable success in identifying extended sources that automated algorithms miss. Projects like Radio Galaxy Zoo have recruited hundreds of thousands of participants who examine radio images and mark features including jets, lobes, and host galaxy identifications. This human pattern recognition capability excels at recognizing faint extended structures and distinguishing genuine sources from artifacts, complementing automated methods. Expanding such projects to new surveys including deep LO-far observations, and eventually ESCA data will leverage public enthusiasm for astronomy while advancing scientific discovery. Giant radio galaxies identified through citizen science contribute to professional research and sometimes bear names chosen by their discoverers,